Now, as always, don't forget that I sell my perfect answer revision guides on my website. If you click on this card, you'll be able to go and purchase yourself a copy. It is available now in all 3 sciences. So if you enjoy my videos and you enjoy the way in which I describe and explain things, that is where you will find a distillation of my videos. You'll also find information about revision courses if you're keen on attending, school licenses and private tuition. However, enough about that, let's get started. So we're going to start by looking at solids, liquids and gases. So when we look at solids, liquids and gases, be prepared to draw their particle diagrams. Notice that solids have particles which are in very fixed arrangements, and that's because the particles vibrate around in fixed positions, they have little kinetic energy and there are strong forces between them. Moving to liquids, you see that the particles are slightly more widely spaced apart, they're not touching quite as much, so they have intermediate forces between them and they vibrate more and they don't have fixed positions. Gases now, so you need your particles to be further apart. This is because they have large amounts of kinetic energy. Obviously they're not held in fixed position and there are weak forces between the particles, and here's your summary now. Let's start naming the correct conversions between all these various states of matter. So remember, if you're going from a solid to a liquid, that is melting, like a solid ice block turns into water, melting. If you go the other way and the water turns into ice, clearly that will be freezing. If you have a liquid and it turns into a gas, that will be boiling or evaporating. And then when you have a gas and it turns back into a liquid, that is condensation. So that's what happens when you have a shower and you see it getting all misted up on the windows. Condensation is occurring here. Touching slightly more on evaporation, so how does the evaporation of a puddle or any liquid happen really? So what you find is that the particles have differing kinetic energy. Now those particles with the most amount of energy will evaporate first and they will leave the surface of the liquid. And what will happen is it will mean that the remaining particles have lower average kinetic energy. Do notice that in a closed container, condensation and evaporation will be occurring simultaneously, which means at the same time. The specification now touches on diffusion, which you should be aware from biology. So diffusion is the net movement of particles from an area of high concentration to an area of low concentration. And because that's down the concentration gradient, you find that no energy is required. It is a passive process. So that means in any scenario where you have large amounts of particles in one place, they will drift and move across to somewhere, some region which has a lower density or concentration of these particles. And the example we like to look at in chemistry is, you might have seen your teacher go through it in class. You've got this huge glass tube and one end you have ammonia, the other end you have hydrochloric acid, and effectively their concentrations are high at either end of the tube, and obviously the particles start to diffuse. So the ammonia starts to move towards the hydrochloric acid, and where they meet, a chemical reaction takes place and ammonium chloride is produced, which we see as a white ring. Now, the location at which this white ring occurs will tell you something about how quickly diffusion is happening, because clearly if the white ring occurs in the middle of the tube, it means that the ammonia and the hydrochloric acid diffused equally quickly across. However, this isn't true. What actually happens is that the ring forms much closer to the hydrochloric end, and that means that the ammonia has diffused further and faster. And what is the reason for this? It's simply because it has a lower relative atomic mass. Looking at some fundamentals which underpin chemistry, we need to look at an atom, element, mixture and compound. So an atom is the smallest particle of a substance that can exist. There are probably more accurate definitions for this, and that will involve high level physics, but for all intents and purposes for your chemistry GCSE, this is what you need to know. An element contains only one type of atom and it cannot be split by any chemical means. So basically, if you're given a list of substances and you're asked which is the element, cross-reference the list to the periodic table and you'll soon be able to see if what you have is an element or not. If it's not in the periodic table, it is not an element. Compounds now, well, that's when you have two or more elements which are chemically combined, and what that means is you cannot separate them back into their constituent elements. And a good analogy for this is when you make a cake. So you add flour, eggs, sugar, and effectively when you bake it, it turns into a cake, and that's the equivalent of a compound, because there's no way you can separate those cake particles back up into eggs, flour, sugar. That's not going to happen, and that's due to the chemical reaction that's taken place. A mixture is different to this. A mixture contains, as you would imagine, 2 or more elements, this time not chemically combined, so theoretically you should be able to separate your mixture into its constituent components. And now I'm just going to bring up an example table showing elements, compounds and mixtures, and you should have a go at potentially separating them out yourself and make sure you can tell the difference. Back to basic chemistry then, so we're looking at periodicity. I've already told you then atom is the smallest part of a chemical element which can exist. So what is a molecule? Well, that is 2 or more atoms bonded together, and the atoms could be the same element, such as H2, so hydrogen, or it could be different elements such as carbon dioxide, but the point to notice is that with a molecule, it's just 2 atoms stuck together. So looking at the structure of an atom, remember that we have the nucleus in the middle, that contains the protons and the neutrons. Surrounding that we have circles which we call shells, and these are shells of electrons. Do remember when you're drawing electronic configuration diagrams that the first shell can contain a maximum of 2 electrons, and after that you can contain a maximum of 8. So let's compare the masses and charges of protons, neutrons and electrons. So protons and neutrons both have a mass of 1, so they're much heavier than electrons, and that's why we say most of the mass is found in the nucleus of an atom. An electron has a much smaller mass, and different examples will say different things, but I tend to say that it has a mass of 1 divided by 2000, so a very small number indeed. Looking at the charges now, neutron, so neutral, has no charge because it is neutral. A proton, positive, has a positive 1 charge, and an electron has a -1 charge. So when we look at an atom, we know that it is uncharged, which therefore means it must have equal numbers of electrons and protons. When we look at the periodic table, you must be really familiar with how to use the periodic table and what it's telling you. So make sure you use the key, because that will tell you which is the mass number and which is the atomic number, but generally speaking the top number tends to be the mass number and the bottom number tends to be the atomic number. So the atomic number is actually the number of protons found in an atom. So for carbon that would be 6, and I told you already that atoms are neutral, which means their proton number equals their electron number, which means the electron number of carbon will also be 6. And if we draw the electronic configuration diagram, we know that 2 electrons go into the first shell and the remaining 4 go into the second shell. Now looking at the mass number, now the mass number is the total number of protons and neutrons. So if carbon has an atomic number of 6, that means the proton number is 6, it has a mass number of 12, that means you can work out the neutron number by taking the atomic number away from the mass number, so the neutron number of carbon is 6. Small thing to notice is the nucleon number, and that's just the total number of particles found within the nucleus of an atom. So it's the total of the protons and neutrons, i.e. it's also the mass number, so they're very closely linked. Going back to the periodic table then, looking at group numbers and period numbers. So the group numbers are the numbers that run along the top of the periodic table. The group number corresponds to the number of electrons in the outer shell. So group 1 elements will all have 1 electron in the outer shell. Now the period numbers run down the side and they refer to the rows, and the period number will correspond to the number of shells of electrons. Why do elements in the same group tend to have the same chemical properties? That's due to the number of electrons in the outer shell. So the answer here is because they have the same number of electrons in the outer shell. So why do fluorine and chlorine behave similarly? Because they're both in group 7 and therefore they both have 7 electrons in their outer shell. Let's look at group 0 now. What is their name otherwise known as? It is the noble gases. And why are they so unreactive? And that's because they have full outer shells, which means they don't really want to get involved in bonding. As a quick overview of the periodic table, do notice there's a step line on the right hand side, and therefore the metals occur on the left hand side of that step line, and the non-metals appear on the right hand side, with hydrogen appearing by itself at the top because it behaves very differently from all other elements. Isotopes now. So if you look in the periodic table, you will see that some mass numbers aren't whole numbers, such as chlorine, which is 35.5, and that's because chlorine exists as an isotope, which means that some chlorine atoms have a high mass number of 37 and other ones have a mass number of 35, and when you work out an average you actually find that it's 35.5, and that's because there are far more chlorine 35s compared with chlorine 37s. However, you just need to know the definition of an isotope, which is that it is atoms of the same element with the same number of protons but different number of neutrons. So how is an ion formed and what is an ion? So an ion is a charged particle which is formed from either gaining or losing electrons. So clearly if they lose electrons, they lose negative charge, so therefore they become positive. If they gain electrons, they gain negative charge, so they become negative.
Remember that in an ionic bond, you've got both a metal and a non-metal, and that's super important because they're what's going to form the ions. Now the metals always form positive ions, whereas the non-metals always form negative ions. In our first example, we're going to do an ionic bonding diagram of sodium chloride. Now, the first thing you want to do is draw the electronic configuration for both elements. So let's start with sodium, which is over here. Now, 11 is the atomic number of sodium, which is also the same as the proton number and the electron number. So we know we need to draw an electronic configuration that contains 11 electrons. So I'm going to start by writing the symbol of sodium in the middle. Now when you're drawing electronic configurations, remember that the first shell, the first circle, can contain a maximum of 2 electrons. And then after that, it contains a maximum of 8, which we arrange in pairs. So we know we need to draw 11 electrons in total. There's the 11th. Now it's time to look at chlorine. Chlorine is a halogen, it's in group 7, so it contains 17 electrons. So we'll start by writing the symbol for chlorine in the middle and then add our shells of electrons. And now we need to draw 17 electrons. We usually use circles or dots to represent the fact that the electrons come from a different element. Now with ionic bonding or any type of bonding, what you're really looking for is for the atoms to have a full outer shell. So let's take a step back and work out what would make sense here. So really that sodium needs to lose that final electron and chlorine needs to gain an electron so that it will have 8 electrons in its outer shell. That electron from sodium transfers itself to chlorine here. So in your final answer in the exam, you'll be asked to draw the ions which are formed, and it always looks like this. You want to start with square brackets. You want to draw the outer shell. You don't need to worry about drawing the inner shells, but it's perfectly fine if you want to do that, showing that it has a full outer shell. Because this is the new outer shell for sodium. Now it's lost an electron. Remember that an electron has a 1- charge, so in effect that sodium is now positively charged, which we draw as that. Now we're going to redraw chlorine. So we'll add those electrons in the outer shell again, making sure that we acknowledge that that final electron has come from a different atom. It's come from sodium, and that's why I've drawn a cross. Because chlorine's gained an electron, it's now Cl-. So that's why we write that charge there, and that is your final answer. If you're asked to draw an ionic bonding diagram for sodium chloride, this is your final answer. Now we're going to do a second example. Now we're going to draw magnesium fluoride. So let's have a look at magnesium in the periodic table. It has 12 electrons. So magnesium has 12 electrons. Now we need to look at fluorine in the periodic table. Here it is. It has 9 electrons. So now we're ready to work out what's going to happen. Well, we know that the magnesium needs to lose 2 electrons. So one of those electrons will be transferred to here. However, fluorine only needs to gain 1 electron, which means we have a spare electron over here. So what are we going to do with that? Well, the thing that makes most sense is if we draw another fluorine atom. And so that second electron is going to be transferred to here, meaning that the magnesium now has a full outer shell here, has 8 electrons, and the fluorine atoms will now have full outer shells. So I'll now draw the final answer for you. So again, we only need to draw that outer shell, which is now this one. It's nice and full, it contains 8 electrons. Notice that it's lost 2 electrons, which remember have a negative charge, which means that the magnesium will have a net positive charge, which is 2+. Now we can draw the fluoride ions. So label those fluoride ions, show those full outer shells with that final electron that's come from magnesium. Because both fluoride ions have gained an electron, they've gained a negative charge. And you do want to notice that these charges for the non-metals should equal the charges from the metal, and that's your final answer. In our third and final example, we're going to look at aluminium oxide. Aluminium sits here, it has 13 electrons. Oxygen has 8 electrons. Now this one's slightly more difficult because if we have a look at what's going to happen, we know that aluminium needs to lose these 3 electrons. So it's quite straightforward to know that those 2 electrons will go here. However, what's going to happen to this electron? Well, we'll need to draw another oxygen atom to accommodate it. But now we have an issue, which is that this oxygen outer shell will only have 7 electrons, so it's missing an electron here, which means we need to draw a whole new aluminium atom over here. So that electron will go over here. We've still got issues, which is that we have 2 spare electrons over here. So guess what? We need to draw another oxygen atom. However, at this point we should be done. So we're actually ready to draw our final answer with the square brackets. And I'll draw it here on the right hand side, quite small, so you can see the working together with the answer. So here's our aluminiums, there's 2 of them. Let's label them. As we expect, they have a full outer shell. Now in terms of their charge, notice that they've both lost 3 electrons, which means they have a net positive charge of 3. Now we're ready to draw oxygen, so we know we need 3 of them. Label them, show that they have a full outer shell. Remember that they each gain 2 electrons from aluminium. They've each gained 2 electrons, so that means they have a 2- charge. And double check, look, 6+ on this side, 6- on this side, so we're sorted, and that is your final answer. Looking at covalent bonding now, we can see we're looking at 2 non-metals, so don't be tempted to draw an ionic bonding diagram. We're going to take a nice straightforward example to begin with, which is water, H2O. So we're going to have a central oxygen atom, 2 hydrogen atoms coming off the side. Label the atoms and then have a look in the periodic table and see how many electrons they have in the outer shell, and remember that's given by their group number. So hydrogen has 1 electron in its outer shell, oxygen has 6, 4, 5, 6, and now double check and see that they're both full. Oxygen now has 8 electrons in its outer shell. Hydrogen only has 2, but that's fine because remember the first shell only needs 2 to become full, so that is now a perfectly completed covalent bonding diagram. Let's look at methane now, which is CH4, which you need to know for organic chemistry. So try and arrange this nice and symmetrically. That isn't particularly symmetrical, but it will do. So again, hydrogen has 1 electron in its outer shell, so let's start by filling in those ones. Carbon is in group 4, so it has 4 electrons. And actually that's already done because now hydrogen has 2 in its outer shell. Carbon has 8, so that is now correct. Carbon dioxide is trickier, and I'll show you that example now. So remember, that's CO2. Remember with this one that it has double covalent bonds, and that will really help you with your answer. So carbon has 4 electrons in its outer shell, but I'm drawing it like that because I know it's a double covalent bond. Oxygen has 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And they both need to have 8 electrons to be full. So carbon has 8 electrons as 2 shared pairs, and oxygen has 8, so that is correct. The most difficult example you could be given is ethene C2H4. So I'm going to show you how to do that. There's your central carbon atoms. Here's your 4 hydrogens. Label them. It's easiest to start with the hydrogens here, remembering they have 1 electron in the outer shells. Carbon has 4, so let's make sure that hydrogen's happy first of all. So 1, 2, 3, 4. Let's do the other side. 1, 2, 3, 4. And now have a look. Yes, all the hydrogens have 2 electrons in the outer shell, and each carbon now has 8, so that is correct.
Let's now take a look at the chemical structures part of the specification, and when we're talking about chemical structures, we're talking about 4 main structures. That is giant covalent, giant ionic, giant metallic and simple molecular, and you need to know and understand why they have various properties such as either high or low melting points, electrical conductivity, that sort of thing. But we're going to start initially with giant ionic structures. So remember, these are made up of a metal and a non-metal. And what is an ionic bond? Well, it's the electrostatic forces of attraction between oppositely charged ions. So remember that the metal ion is positive and the non-metal ion is negative, and therefore they attract. So why do giant ionic structures have such high melting and boiling points? And that's because they have strong electrostatic forces of attraction between oppositely charged ions. And don't forget to qualify this by saying that they require a lot of energy to break. Why don't they conduct when solid? That's because the ions aren't free to move. Why do they conduct when they're molten or liquid? That's simply because the ions are free to move to carry the current. Why are they brittle? And don't forget that brittle means that they smash easily when hit. That's because when you hit them, or when a force is applied, the layers of ions slide, so the ions with the same charge end up next to each other. So positive charges will therefore repel and the whole structure breaks apart. So that's giant ionic done. Moving on to giant covalent, and we are really looking at carbon here. So we're looking at diamond and graphite, which remember are both forms of carbon. So the definition of an allotrope is different forms of the same element. So why does diamond have such a high melting point? And that's because it has a giant tetrahedral structure, which really means that each carbon atom is bonded to 4 others. So it has many strong covalent bonds, which require a lot of energy to break. Why does graphite have a high melting point? Similar argument, but this time each carbon atom is bonded to 3. You still have many strong covalent bonds and it still requires a lot of energy to break, but because it's bonded to 3 rather than 4 carbon atoms, that's why graphite has a slightly lower melting point than diamond. Why is graphite used as a lubricant? That's because the carbon atoms are arranged in layers with weakened molecular forces between the layers. These require little energy to break, and therefore the layers can slide off each other, hence it's used as a lubricant. Why doesn't diamond conduct electricity? And that's because it has no free electrons. However, graphite does conduct electricity, the reason being that each carbon atom, as we've already said, is only bonded to 3 others, meaning that there's a 4th electron which is free to move and therefore carry the current. We should touch on a covalent bond here. Now remember, a covalent bond is a shared pair of electrons. If you want to be more complex about it, you can say it's the electrostatic attraction between the positive nucleus and the shared pair of electrons. Why do simple molecular substances have such low melting points? and that's because they have weak intermolecular forces which do not require a lot of energy to break. A small point to note, which is why do simple molecular substances have increasing boiling point with increasing MR? So remember, MR is the relative atomic mass, so it's really saying something like, why does ethane, C2H6, have a higher melting point than methane, CH4? And that's because ethane, so substances with a greater MR, have greater intermolecular forces of attraction between molecules, and these require a lot more energy to break. And remember, when you're boiling these substances, you're not breaking apart the individual atoms from the molecule, you're simply separating one molecule from another. So you're breaking intermolecular forces. Lastly, giant metallic structures. So these are just the metals you find in the periodic table. Remember, they have high melting points. That's because they have strong metallic bonds, and a metallic bond is simply the attraction between a positive ion and the delocalized electrons. So if you had to draw the structure of a metal, keep it nice and simple. Just draw a rectangle to represent the metal. Draw some positive ions evenly arranged with a sea of delocalized electrons surrounding them, and that will be sorted. Why are metals or giant metallic structures such good conductors of heat? And that's again due to delocalized electrons. What's that noise? Which are free to move and carry the heat throughout the structure. Why do metals conduct electricity? Again, that's because they have a sea of delocalized electrons which are free to carry the current. Lastly, two other properties: the fact that metals are malleable, which remember means that they can be hammered into shape, and that they are also ductile, which means they can be drawn into a wire. The reason for both of these properties is because the layers of ions can slide over each other.
I'm going to show you my favourite method of balancing equation, which always works. So if you can't actually see straight away how to balance them, use this method and you'll be able to balance any equation. So start by doing a dotted line and then list the elements present on each side of the equation, and obviously they ought to be the same. So we've got hydrogen, nitrogen, oxygen, calcium, and then just copy that straight over and line it up nicely. And now we want to do a tally chart to show how many of each element we have. So count the hydrogens on the left hand side of the equation. So we've got 1 present in the nitric acid, 2 present in the calcium hydroxide, so that's 3. The number of nitrogens is 1. The number of oxygens, well, 3 on the nitric acid side, and then you've got 1 inside the brackets, but the 2 after the brackets means that there's 2, so add those up all together and it's 5. Now the calciums is just 1. Now we need to do the same for the product side of the equation. So how many hydrogens do we have? Well, that's 2, which is present in water. Oxygen, you've got 3 present in calcium nitrate, but remember that small 2 after the brackets means that's doubled, so that's 6, plus 1 found in water, so that's 7. Nitrogen, you've got 2. And calcium you have 1, and now we need to have a look at our tally charts and see what the issue is. So the calcium are fine, the nitrogen are not fine. You've got 2 on the right hand side, 1 on the left hand side, so we're going to add a big 2 in front of nitric acid. Remember, when we're balancing equations, all you're allowed to do is add big numbers. And now readjust your tally. So you now have 4 hydrogens, 8 oxygens, 2 nitrogens. So the nitrogens are happy, the calcium is happy, but the oxygen hydrogens aren't. So I'm going to put a 2 in front of water to make that 4 hydrogens. And now adjust the oxygens, so you now have 8 oxygens. And look, the whole thing is balanced because you have 4 hydrogens on both sides, 2 nitrogens, 8 oxygens, and 1 calcium. So that is indeed balanced. Unfortunately, there are some ions which you'll simply have to learn off by heart because you can't work them out from the periodic table. So let's just go through what all of these are. Starting with these transition metals along here, just going to have to learn them. The first one is silver, this one is copper, Pb2+ is lead, and zinc is Zn2+. Notice with transition metals like iron that have variable valencies, you'll be given it in the question so you can actually see what their charge will be given by the Roman numerals. So that's not something you need to remember. This is the ammonium ion. And now looking at the negative ions, if it's combined with oxygen, it tends to have 8 in its name. So this is carbonate, sulfate and nitrate, and that final ion is hydroxide. So now we can get started on some examples. So starting with magnesium chloride, so let's write down the ions. We can see from the periodic table that magnesium is in group 2, hence Mg2+. Chlorine is in group 7, so 8 minus 7 is 1, hence Cl-. Now have a look, they're not balanced obviously. You've got a 2+ and a 1- charge, so clearly you need 2 chlorines. Remember, when you're writing the formula, you write a small number after the element in question, which is why this is the formula of magnesium chloride. So lead hydroxide, these are both ions you're going to have to learn off by heart. So Pb2+, OH-. So we've got the same issue here in that we don't have enough minus, so you need 2 OHs. So you're going to write PbOH2. However, the 2 applies to both the oxygen and the hydrogen, which is why you need brackets. So insert brackets, and that is your formula. Now lithium is in group 1, so it has an Li1+ charge. So it has a 1+ charge. Oxygen is in group 6, 8 minus 6 is 2, so it's O2-. This means you need 2 lithium for every oxygen, so Li2O. Magnesium nitrate, magnesium is in group 2, so Mg2+. Nitrate you've got to learn from the list above, NO3-. You've got a 1- charge with nitrate compared with the 2+ charge on the magnesium, which explains why you need 2 lots of that nitrate, and you need to insert brackets again. Don't touch this 3 here, that just remains part of the formula. People get confused and start moving it around. No, that is the final answer. Lastly, aluminium in group 3, 3+. Learn sulfate's charge, which is SO4 2-. This is a difficult one now. It's not that clear. You've got to find a common number that both 3 and 2 go into, which is 6. So if I show you my thought process, I effectively need 2 aluminiums and 3 sulfates to make it equal 6, because now we have 6+ on the aluminium side, 6- on the sulfate side. So that's therefore Al2, SO4 3, not forgetting the brackets as usual. Now, if you don't like the method I just showed you, there is a cheats way of doing it where you don't actually have to understand the chemistry. What you do is you write out the ions as usual. So potassium is in group 1, hence 1+. Oxygen is in group 6, 8 minus 6 is 2, so 2-. And all you have to do here is swap and drop. So literally bring down that invisible 1 to here, that 2 to there, and then rewrite the ions. So your final answer is K2O. And it works with anything really. So let's do aluminium nitrate. Aluminium's in group 3. Nitrate we've learned off by heart from the list above. We're going to swap and drop, so we're going to bring that 3 down. We're going to bring that invisible 1 down. And so it becomes AlNO3, 3, because you brought that 3 down.
Relative atomic mass I've already described a little bit, but you do need to be able to define it, and that is that it's the ratio of the average mass of an element when compared with one atom of carbon-12.
Looking at more calculations now, use the formula triangle to help you rearrange, and you can see that mass is therefore given by the relative atomic mass, which is mR, times number of moles. Moles is going to be mass over mR, and that's a good way of rearranging without too much effort. So let's get started and have a look at some examples. So first of all, we're just finding the MR of calcium hydroxide, and that's just a matter of looking up the various masses in the periodic table. It tends to be the top number and adding them all together. So if we have a look, we see calcium is 40, oxygen is 16, but we have to times it by 2 due to this small 2 here. And then we add hydrogen, which is 1, and again times it by 2. Pop that into your calculator. And you get an MR of 74. Now looking to find the number of moles in 5.4 grams of calcium carbonate. So I like to write out the equation I'm using, it's good practice. Stops you making silly mistakes. So using my formula triangle, I see it's mass divided by MR. We've been given the mass in the question, which is 5.4. Now we need to work out the MR of calcium carbonate. So using the periodic table, calcium has a mass of 40 carbon is 12, oxygen is 16, and we need to multiply that by 3 due to this 3 here. So that's 5.4 divided by 100 of 0.054. So the empirical formula is the simplest ratio of atoms of each element present in a compound. And just to make that really clear what that actually means, we need to look at the molecular formula at the same time, because although they sound very similar, and indeed they are very similar, they have slightly different definitions. So the molecular formula is the actual number of atoms of each element present in a compound. So let's take propene as our example here. So looking at its molecular formula, what is the actual number of atoms of each element present in propene? Well, we know it contains 3 carbon atoms. It obeys the general formula CnH2n, which is why its formula is C3H6. That is its molecular formula. However, if we look back at our definition of an empirical formula, we're looking for the simplest ratio. So basically we want to cancel this down. Now we can see by looking at the molecular formula of propene that 3 goes into it. So we want to cancel by 3, means we'd have CH2. And that is our empirical formulae, and that's actually what we're going to be looking at calculating now. So in question 1, a compound contains 40% carbon, 6.73% hydrogen and 53.2% oxygen by mass. Determine the empirical formulae. So first of all, start by listing your elements. So we've got carbon, hydrogen and oxygen. Make a table, and you want to write mass, MR and number of moles down the left hand side. So the mass we've been given in the question, although it says all the masses in percentages, it doesn't matter because effectively they're all ratios. So you could have 40 grams of carbon and that would still be 6.73 grams of hydrogen, which is why we're allowed to write down the numbers exactly as they are. Then use your periodic table to look at their atomic masses. You'll see that carbon has a mass of 12.01, hydrogen has a mass of 1.01, oxygen has a mass of 16 exactly. Now using this formula triangle, which hopefully you'll be very familiar with, we have mass at the top, MR and number of moles at the bottom. So if we cover the one we're after, which is number of moles, you can see that that is given by mass divided by MR. So when we look at the third row of our table, that's the exact calculation we're going to be doing. So first of all, for carbon, divide 40 by 12.01 to get 3.33. To get the number of moles of hydrogen, do 6.73 divided by 1.01 to get 6.66. And lastly, for oxygen, do 53.27 divided by 16 to get 3.33. And now at this point, you want to have a look at those 3 numbers and then choose the smallest one and divide all the values by the smallest number. And as we can see, that will be 3.3. So we're dividing every single value by 3.33 to get our ratio of 1 to 2 to 1. Now don't forget to answer the question. We're looking for a formula, so we have a final formula which is CH2O. Now I'm going to show you a water crystallization type of mole calculation. It's really similar to empirical formulae, so don't let it freak you out just because it looks more difficult. So 35.75 grams of sodium carbonate combined with water are heated strongly and 13.25 grams remain after heating. Calculate X. So obviously after you've heated it, it will now become anhydrous, which means you've driven off the water. So lay it out like the table again, Na2CO3, but instead of listing the elements, you're just going to have the various components of the question. So it's just going to be sodium carbonate on the left, water on the right, and then mass, MR, and moles as usual. So we know that 13.25 grams of the sodium carbonate remain after heating, which is why this is the number here. Going to have to do a small calculation to work out the amount of water that was lost. So that's 35.75 minus 13.25 to get 22.5. The MR, use the periodic table, so we'll see sodium is 23, times it by 2 because of that small 2, plus carbon's 12, plus 3 lots of oxygen, which is 16, to get an MR of 106. And I know off by heart that the MR of water is 18, and you can check that in the periodic table if you don't believe me. To work out the number of moles now, mass divided by MR, giving us 0.125. This is 1.25. And then divide by the smallest number, which is clearly 0.125. So that will obviously be 1. This is 10. Therefore, X equals 10, and that's it. It's very similar to the empirical formulae question. Now we need to look at reacting mass and gas volume questions. So 3.3 grams of hydrochloric acid react with sodium carbonate. Calculate the mass and volume of carbon dioxide collected. Now, I do imagine that in your question paper they'll give you the balanced symbol equation, which is the starting point of this calculation. However, in another part of the exam paper, they could easily expect you to write out your own salt equations and to balance them, which is why I'm going to do all of that right now. So hydrochloric acid reacts with sodium carbonate to produce a salt, which is sodium chloride, plus water, plus carbon dioxide. Make sure it's balanced. I know I need a 2 there and a 2 here. And now we need to use the table format in order to help us answer the rest of the question. So mass, MR, and moles. And don't forget to use your formula triangle down here, which is mass, MR, moles. And this is how I always set myself up to make sure I'm going to get the question right. So what have we been given in the question? Well, we know 3.3 grams of hydrochloric acid reacted, and we know we need the volume and mass of carbon dioxide, which is why my X goes here. Now the MR, use the periodic table. Now make sure you're just adding up the hydrogen and the chlorine. You're not including the 2 in this. So it's just 1 plus 35.5 equals 36.5. The MR of carbon dioxide is going to be 12 plus 2 lots of 16, which is 44. Using the formula triangle, we see that moles is mass divided by MR. So we do 3.3 divided by 36.5 to give us 0.09044109. And now remember, what we can do here is carry that number across to be the number of moles of carbon dioxide. Do check the big numbers up here. Now there's 2 lots of hydrochloric acid compared with only 1 lot of carbon dioxide, which is why in order to carry over the moles we have to actually divide 0.09041 by 2. And that becomes 0.045205. And now we're ready to work out the unknown mass of carbon dioxide, which is mass equals MR times moles. We've already calculated the MR, which is 44. Moles is 0.045205. And that is 2 grams to 3 significant figures. Why is it so noisy in London everywhere? Now to make sure we're answering the second part of the question, which is to do with gas volumes, make sure you know that 1 mole of any gas occupies 24 decimeters cubed. So we know the number of moles of carbon dioxide. We've already calculated that, which is 0.045205. Therefore, to work out the volume, simply times that by 24. Becomes 1.08 decimeters cubed. So that's the answer to the second part of the question. Do notice that they could have asked you it in terms of centimeters cubed, and in order to convert decimeters cubed to centimeters cubed, you just have to times by 1,000. So just times that number by 1,000, and therefore your answer here is 1,080 centimeters cubed to 3 sig fig. 3.2 grams of copper reacted with 0.4 moles of nitric acid. Which reagent is in excess? Don't worry too much about this. We're going to use the same method as always, which is the table format. So we're going to write mass, MR, and moles down the left-hand side. And remember our triangle, which I'll put here, which is mass at the top, number of moles, and MR. So we know that 3.2 grams of copper reacted. And weirdly, we're going to put X here because that is important, and I'll say why soon. So first of all, what is the MR of copper? Using your periodic table, you see it's 63.5. So using your formula triangle, how do you work out the number of moles? You do mass divided by MR, so that's 3.2 divided by 63.5 to get 0.05 mole. And then have a look at the big numbers. We've got an invisible 1 here, we have a 4 here, and I've already taught you, you just need to pull that number across, but instead times it by 4, so you get 0.2 moles. So now we compare, we have a look, and we have a look at what we were given in the question. Well, we were told we had 0.4 moles of nitric acid, but we only need 0.2, so clearly nitric acid is in excess. Now we're looking at percentage yields. So for example, in a reaction, 11.2 grams of copper sulfate was obtained when theoretically 12.5 should have been obtained. Calculate the percentage yield. So you just need to use this equation here, which is percentage yield equals actual yield over theoretical yield times 100. So the actual yield here was 11.2, the theoretical one was 12.5, multiply it by 100, and you get a value which is 89.6%. Now they can be more difficult than this, so I'm going to show you that example now. So let me talk you through a slightly more complicated version. So a student reacted 2.4 grams of copper oxide with sulfuric acid. She made 1.8 grams of copper sulfate. Calculate the percentage yield. So as always, we need to start with a balanced symbol equation. So that will be copper oxide plus sulfuric acid, which is H2SO4, forms copper sulfate, CuSO4, plus water. And then step back and double check that it is balanced, and it is. And we're going to use my favourite table as well, obviously, because I never do a more calculation without it. So let's start with what we know. We know that we have 2.4 grams of copper oxide, and we have made 1.8. So that is the actual yield, and we need to find out the theoretical yield, which is why I'm going to put an X here. So now it's just a matter of working out the MR of copper oxide. So do 63.5 plus 16, so use your periodic table for that to work out that its MR is 79.5. To work out the number of moles, simply do the mass divided by the MR, so that's 2.4 divided by 79.5 to give a value which is 0.0302 moles. Now we need to look at the balanced symbol equation and have a look if there are any big numbers. There aren't, so we can easily just carry that number across to be the number of moles of copper sulfate. Now work out the MR of copper sulfate, so you want to do 63.5 plus 32 plus 4 times 16. So that gives us an MR which is 159.5, and then we work out X by doing 159.5 times by 0.0302 to get 4.8169 grams. And now we can just substitute that into our percentage yield equation because that is the theoretical yield. So percentage yield is given by actual yield over theoretical times by 100 because we're looking for a percent. So actual was 1.8, theoretical was 4.8169, times that by 100, and we get a value which is 37%.
Let's look at titration calculations now. So 25 centimeters cubed of 2 mole DM-3 hydrochloric acid reacted with 30 centimeters cubed of sodium hydroxide. Calculate the concentration of sodium hydroxide. You need your balanced symbol equation for this, which again I think they'll give you, but you do need to be able to do this as a separate skill, which is why I'm going to do it now. So the salt made is sodium chloride and water is the byproduct. Double check to see if it needs balancing, and it doesn't. And then to be clear, make sure you use this formula triangle now, which is number of moles goes at the top, concentration and volume go at the bottom, and therefore titration calculations will be really straightforward for you. So just make sure in your table this time it goes moles, concentration and volume, and then substitute in what you know from the question. So your concentration of hydrochloric acid is 2 moles DM-3, so that's going to be 2.
The volume we've been told is 25. Now, to make sure you don't screw up these questions, make sure you convert that straight into decimeters cubed. So I do that by just writing divide by 1,000, so I know what to put into my calculator. We know the volume of sodium hydroxide is 30, so I'm going to do the same here. Make sure I've divided it by 1,000 in order to account for the fact it needs to be in decimeters cubed, and then we're looking for the unknown concentration of sodium hydroxide. So the moles is concentration times volume. I can see that from the formula triangle. So let's work out the number of moles of hydrochloric acid. So 25 divided by 1,000 times 2, which is 0.05. Have a look at any big numbers. There aren't any, so that means I can carry that number straight over, and that becomes the moles of sodium hydroxide. To work out this unknown concentration, we have to do moles divided by volume. We can see that from the formula triangle. So we do 0.05 divided by 30 over 1,000. Just pop that all into your calculator as it is. And you get an answer which is 1.6 recurring. So that rounds to 1.67 moles dm to the minus 3 to 3 sig fig. So here's an example of the sort of questions you might be asked in the exam. A student does a titration to find the concentration of a solution of hydrochloric acid. The student titrates 25 centimeters cubed of hydrochloric acid with sodium hydroxide solution of 0.2 moles. The equation for the reaction is: the student added 28.6 centimeters cubed of sodium hydroxide to neutralize the acid. Calculate the concentration of hydrochloric acid. So what I would do is do exactly what I was just doing in my talk through. So make sure you have the balanced equation here. Make sure it's balanced. Just double check that the elements are the same on each side, and then remember your triangle is NCV, and then I'm going to write that down the side here, and remember I like to do it in like a table format. Next up I'm going to write an X over the thing that I'm looking for, which is the concentration of hydrochloric acid, so the X is going to go here. Then I'm going to include what I've actually been told in the question. So I've been told that 25 centimeters cubed of hydrochloric acid reacts. And remember, in these calculations I need to convert it into decimeters cubed, so I'm just going to write a divide by 1,000 there. I've also been told the volume of sodium hydroxide solution, so that's 28.6, so that's going to go here. And I'm going to divide it by 1,000 for the same reason. Okay, now looking back, I've been told the concentration of sodium hydroxide, so that's going to be popped in here, and now I'm ready to calculate the number of moles, and using my triangle I can see that number of moles is concentration times volume. So into your calculator you need to put 28.6 divided by 1,000 times by 0.2 to get 5.72 times 10 to the minus 3. Now because there are no big numbers in front of the hydrochloric acid or the sodium hydroxide, I know that the number of moles of sodium hydroxide is the same as the number of moles of hydrochloric acid. So I'm going to copy that number across here. Sorry, it's so small. Definitely need more space. And now I need to find the concentration because that's what X is. So concentration, using the triangle again, is number of moles divided by volume. So I'm going to divide that number. I've kept it in my calculator display. I'm going to divide it by 25 divided by 1,000, and X is 0.2288. So there's my answer, and I'm going to just write that answer to 3 significant figures into the answer box. Yay, done. Now, some calculations will want you to convert between the number of atoms to the moles to the mass, and I definitely think that using this arrow system at the top of this page is the most straightforward way of doing this. If you write it out, it basically leads you the right way to the correct calculation. The only thing you need to remember is the value of Avogadro's constant, which is 6.02 times 10 to the 23. And remember, that stands for the number of atoms or molecules which are present in 1 mole of a substance. So let's have a look at a few examples, and hopefully you'll see that this arrow system really works. So in this first example, we're calculating the amount in mole of water in a sample containing 2.30 times 10 to the 3 molecules. So we're looking for the amount in mole. We have been given the number of molecules, so we're looking for moles, which is in the middle of this arrow setup. We've been given the number of molecules, and now we just need to follow the arrowhead to work out what we need to do. And so clearly we need to take the number of molecules and divide by Avogadro's constant. Now let's make sure we lay out your work nicely. So I've written number of moles of water equals, we know it's the number of molecules given, and we need to divide that by Avogadro's constant, 6.02 times 10 to the 23. And this gives us a value which is 0.382 moles. So for question 2, we're calculating the number of oxygen atoms contained in 3 moles of glucose, which is C6H12O6. So this time we're calculating the number of oxygen atoms contained in 3 moles of glucose, C6H12O6. This one's trickier because it's O6, but we'll only start making sure that we haven't made a mistake with that towards the end of this working out. So we're looking for the number of oxygen atoms. So looking at my diagram above, what I need to do that is put number of, I'm going to write molecules because we've actually got a molecule here, C6H12O6, equals the number of moles times Avogadro's constant. Let's substitute in the values. So it's 3 times 6.02 times 10 to the 23. Work that out and it's 1.806 times 10 to the 24. But crucially, that's the number of molecules of glucose, but we need the number of atoms of oxygen. And you can see within that 1 molecule of glucose, there are 6 atoms of oxygen, which is why we need to multiply that number by 6 to get a value which is 1.08 times 10 to the 25.
And in electrolysis, remember you have your giant ionic structure. It needs to be molten or in solution. Why? To allow ions to be free to move so they can carry current. That is essential. So if you have solid sodium chloride and you attach the electrodes to it, you're not going to be able to conduct electricity through that sodium chloride. We've just discussed this in chemical structures because the ions aren't free to move. Putting in solution means that the ions are free to move, so we can carry a current. So those 2 electrodes dip into the substance. Now remember, the electrodes are made out of an inert substance, and that means an unreactive one, which makes sense. You don't want it getting involved in the reaction. So they can be made out of things like platinum or graphite, as these are unreactive. In terms of naming things properly, you've got to remember what an anion and a cation is. So cations are positive ions, anions are negative ions. So remember, opposites attract. So anions, which are negative, will be attracted to the anode, which is positive, and the cation, which is positive, will be attracted to the cathode, which is the negative electrode. So do try and remember that, and I always use PANC to help me remember. Positive anode, negative cathode. Anodes attract anions, cathodes attract cations. So the ode ending is the electrode and the ion is the ion. In terms of remembering what forms where, you need to remember a few rules. So if you have aqueous solution, that makes it more complicated, because as well as, let's take sodium chloride for example, so as well as the sodium and the chloride in solution, you've got hydrogen ions and hydroxide ions, and remember only one of those ions can move to each electrode. So let's take the negative electrode first of all, which is the cathode. That is obviously going to attract a positive ion because opposites attract. Now in order to work out which ion it attracts, remember it is the least reactive element that discharges at the negative electrode. So in the case of sodium chloride with hydrogen and hydroxide, that will be hydrogen, so H+ ions will discharge. And when you're writing these equations, remember you've got H+, you're trying to make it neutral, which is why you have to add E-, you have to add electrons to it, and it will form H2, because remember hydrogen is diatomic. Because you've added electrons, remember this is reduction, so don't forget oil rig. Oil rig is a way of remembering the difference between oxidation and reduction. Oil, so oxidation is loss of electrons, reduction is gain. So in the case of hydrogen, you've got a gain of electrons, so reduction. Now looking at what discharges at the positive electrode, make sure you remember that halogens discharge before anything else. We have a halogen in solution here, a halide ion. It's chlorine, so chlorine will discharge. So Cl- will have to turn into Cl2. The easiest way to see what will happen is because it's minus and you need it to become neutral, you need to remove the negativity, which is why you need to remove E minus. Because you've lost electrons, you've therefore carried out oxidation. And you must practice lots of these questions because this is really quite tricky. Do notice that both hydrogen and chlorine are both diatomic molecules, so you'll be making H2 and Cl2. And remember the other elements which are also diatomic is nitrogen, chlorine, fluorine, bromine and iodine, and oxygen. Now do remember this as a list because in case it comes up and you've got to balance equations, you've got to remember that they're diatomic. And my friend who's also a teacher, she told me a way to remember this, which is horses need oats for clear brown eyes. So hydrogen is horses, need is nitrogen, oats is oxygen, 4 is fluorine, clear is chlorine, brown is bromine, and eyes, it's a bit strange because obviously it's not eyes, it's about eyes, but iodine. Going back to our aqueous sodium chloride example, so I've already told you that hydrogen discharges, chlorine discharges, so left over in solution you have sodium hydroxide, and this is actually a very important industrial process because all three of these products are very useful. Why? Because chlorine is obviously used as a disinfectant, it helps to kill bacteria in drinking water and swimming pools, for example. Hydrogen can be used as a fuel, it's also used to harden vegetable oils to make margarine. And sodium hydroxide is used for making bleach and for making paper.
So we've looked at electrolysis in a lot of detail now, but we're going to go through some various examples and try and work out what is made at the anode and what is produced at the cathode, together with some observations. So let's do this as a table. So don't forget that your anode is positive and your cathode is negative, and I've written those there so we know what's going on. So we've got molten lead 2 bromide to begin with. And remember, that's therefore going to be made up of Pb2 plus and Br minus. And that 2 here has told us that it's 2 plus. Bromine is in group 7. 8 takes 7 is 1, hence why its charge is -1. So remember that opposites attract, which therefore means that at the anode you're going to produce bromine and at the cathode you're going to produce lead. The observations here are that the lead collects at the cathode and it literally just drips off in a molten state, whereas bromine gas is produced at the anode, which bubbles off. Our next example is going to be concentrated hydrochloric acid. What are the ions involved again? That's H plus and Cl minus. Again, opposites attract, which means that at the anode we're going to have chlorine produced. At the cathode we'll have hydrogen. These are both gases and they'll both be bubbled off. Next up we've got aqueous sodium chloride. This is becoming more complicated now because it is aqueous, so we need to list the ions involved. So because it's aqueous, we have H plus, OH minus. The sodium, well, that's in group 1, so we have Na plus. Chlorine is in group 7, 8 takes 7 is 1, so it's Cl minus. And then when we come to look at the product at the anode, remember only one product can be formed. And at the anode, you're going to find that the halogen wins in every single case. The halogen here is group 7. Which is why chlorine is produced here. The product at the cathode, where you're looking for the least reactive element out of the positive ions. So we're looking at hydrogen and sodium. Clearly hydrogen is far less reactive than sodium. Sodium is an extremely reactive group 1 metal, which is why we're going to have hydrogen produced here. The chlorine and hydrogen will be bubbled off, as with the hydrochloric acid example above. Electroplating now, and that's where you cover an object with another metal. You need to know a few things here, which is that first of all, rather than using platinum or carbon as the anode or cathode, what you're going to do here is use the metal that you're coating your object with as the anode, object being coated or plated is your negative cathode. The electrolyte, so the substance undergoing electrolysis, is actually a solution of a soluble compound of the metal. And when electrolysis occurs, what you find is the metal ions are reduced at the cathode. So for example, if we were coating in copper, they would be reduced, which means they gain electrons at the cathode to become copper solid. And as a result, that cathode becomes plated or covered in that ideal metal, which in this case would be copper. So let's look at some uses of electroplating. And really it's because electroplating objects gives them much better properties compared with usual, or it means it's cheaper to have a particular object. So famously, lots of jewellery is electroplated. So things, if you buy a necklace and it says that it's silver plated, that has undergone electroplating. And you tend to find that the actual necklace itself is made out of copper, and then it has a very thin layer of silver over the top. So why would we want to do that? Well, because silver is exceptionally expensive. It's very rare. There isn't very much found within the Earth's crust. Copper is way cheaper. So if you make the bulk of the necklace from copper, add the silver plate, you get the same effect. Obviously, the quality won't be the same. We also coat steel bumpers, so that's a part of a car, with chromium. Chromium is very hard and very shiny, so it's aesthetically really pleasing. It's got great properties, but it's very expensive, hence why we don't make the whole object out of chromium. Lastly, we coat cans or tin cans, which are made out of steel. So a saucer can that you get baked beans out of or something, it will mostly be made out of steel, but it'll have a coating of tin on it because tin is corrosion resistant and won't react with the food contents, which we really don't want to happen, obviously. So remember, a cell is an object which can produce electrical energy. You do need to know that a simple cell is actually made out of two metals and an electrolyte. A redox reaction takes place, which is where reduction and oxidation occur at the same time. And while this is taking place, an electric current is formed. So we know all about fossil fuels as a method of producing lots of energy, but we're looking for cleaner fuels, and one particular fuel we're very interested in is hydrogen. So the reason we're very keen on this as a possible source of energy is because, first of all, it's exceptionally available. It comes from seawater. The reaction that takes place is actually hydrogen reacts with oxygen, forming water. Let's balance this equation. This is a great thing to happen because water is not a pollutant. We need to drink it every day to keep ourselves alive. It's a very clean byproduct, unlike the carbon dioxide, carbon monoxide that comes from burning fossil fuels. This process is going to be carried out using a hydrogen fuel cell. And what you find is that hydrogen is oxidized at the negative pole, which means that it loses electrons. And then conversely, you find that oxygen is reduced at the positive pole. So we're going from oxygen gas to the ion, which is O2 minus. It's reduced, which means it needs to gain electrons. And now we need to balance our oxygens. Because oxygen is diatomic, we need a 2 here. It's reduced, which means it gains, and we need a 4E minus there.
So with the term exothermic, let's define it. First of all, it means the release of heat energy. And remember that more energy was needed to make the bonds in the products than was needed to break the bonds in the reactants. So looking at endothermic reactions, you'll see the opposite. So heat energy in this case is taken in, and more energy is required to break the bonds in the reactants than was needed to make the bonds in the products. Other terms we need to know: activation energy. This is simply the minimum amount of energy required for a reaction to occur. How do catalysts work? Well, we know from biology that they speed up the rate of reaction without being used up. In terms of how they work, it's because they provide an alternative reaction pathway with lower activation energy, and I'll show you some energy profiles so you can actually see that lowered activation energy.
So I thought the easiest way to talk you through the energetics topic was to take you through some past exam questions, because they're pretty much all the same. So the moment you see a polystyrene cup and a thermometer, we're looking at enthalpy. So be aware of what endothermic and exothermic means here. So remember, exothermic means gives out heat energy, and endothermic means takes in heat energy. And with an exothermic reaction, you're looking for a negative delta H, whereas endothermic, you're looking for a positive delta H. Again, in terms of the actual temperature of the beaker or the cup, an exothermic reaction will get hot and an endothermic one will get cold. And if you bear that in mind, hopefully it'll make answering these questions far more straightforward. A student uses this apparatus to investigate the heat energy released when nitric acid is added to potassium hydroxide solution. So we've got nitric acid inside the burette, which is going to be dripped into the polystyrene cup containing potassium hydroxide. She uses this method. Put 25 centimeters cubed of potassium hydroxide solution into the polystyrene cup. Measure the temperature of the potassium hydroxide solution. Add 5 centimeters cubed of nitric acid from the burette. Stir the mixture and measure the highest temperature reached. Add further 5 centimeters cubed samples of nitric acid. Stir and measure the highest temperature reached after each addition. Name the piece of apparatus that should be used to measure the 25 centimeters cubed of potassium hydroxide solution. So you need a fairly precise piece of apparatus here, which is why you should state either a pipette or a burette. Measuring cylinder would not be precise enough. The table shows the student's results. So here she's got the different volumes of acid and the highest temperature reached, and we can see the highest temperature was reached when the largest volume, 30 centimeters cubed of acid, was added. The result for 20 centimeters cubed is anomalous. Suggest 2 possible mistakes other than misreading the thermometer that the student might have made to produce this anomalous result. So remember, anomalous means that it's the odd one out. It isn't quite what you would expect. And if we actually look at those results, it's 31, which is pretty close to 29. So we're thinking that the temperature is too low. So what could have caused the temperature to be too low, aside from misreading the thermometer? Well, first of all, she could have added less than 5 centimeters cubed extra of the acid. Secondly, she might not have waited until the highest temperature was reached. And thirdly, remember, when you're doing this experiment, it's really important that you stir the reactants. So she might not have stirred them properly. Suggest a true value for the temperature when 20 centimeters cubed of acid is added. So let's have a look. You kind of want somewhere that sits between 29 and 37. So I'd probably go in at 33. In another experiment, the student records these results. Volume of potassium hydroxide solution, starting temperature of potassium hydroxide solution, total volume of acid added, and the highest temperature reached by the mixture. And we're calculating the heat energy released using this equation, Q equals mc delta T. So this is really nice. They've given us pretty much all of it. So Q is what we're after. Mass of the mixture, so you need to add those 2 volumes together. So 25 plus 25 is 50. Times the specific heat capacity, which we've been given, is 4.18, times the temperature change, which is, we know it goes from 16 to 35, meaning that there has been a 19-degree increase. And then when you pop that into your calculator, you get a value which is 3970 to 4 significant figures. Let's have a look at some more questions. So explain in terms of making and breaking bonds why some reactions are endothermic. Draw a labelled energy level diagram for an endothermic reaction So this is what you need to do. You need to do your axes here. The y-axis is the energy, and the x-axis is basically the progression of the reaction. So remember, with endothermic, you're looking at a positive delta H, which means that the products by definition must sit at a higher energy level than the reactants. So make sure they are, and then we label them products. We've got our reactants over here. And then just draw an arrow from the reactants to the products going upwards, so delta H is positive. Use the bond energy data to calculate the enthalpy change for the reaction below, making sure to give a sign and units in your answer. Draw a labelled energy level diagram for this reaction. 5 marks. Okay, so this is good. If they haven't drawn them out for you like this, you need to see all the bonds. Make sure you draw out that diagram, otherwise you'll screw up. So it's so important that if they give you it looking like this instead, like CH4 plus 3O2, it is essential that you convert it into a picture like this. So let's have a look at the bonds broken first of all. And so just start by listing the bonds. So we've got CH, and how many do we have? Well, we've got 1, 2, 3, 4, and I do like to cross them off to make sure I've got them all. Then look into the table, and it's 4, 1, 2. Then we've got 1 CC bond, which is 6, 1, 2. And then we've got 3 lots of the oxygens, so that's 3 times 4, 9, 6. Use your calculator to add it all up. These questions are just about being accurate more than how difficult they are. So you must check your answer. So that's 3, 7, 4, 8. Now bonds made. So be careful here. We've got an OC bond, and count how many there are. There are 1, 2, and then there's a big 2 there, which means there's 4 times 7, 4, 3, which I've got from the table again. And then again with the OH, we've got 1, 2, and then the 2 again, so it's 4 times OH. So 4 times 4, 6, 3. And that gives us 4, 8, 2, 4. And then in order to work out this, you need to do 3, 7, 4, 8. Take away 4, 8, 2, 4 to get minus 1076 kJ mole to the minus 1. Be careful with your units. And that reaction is therefore exothermic because it's a minus. Just to show you how to draw the energy level diagram, really similar to what we did above. Here are our axes. We've got energy or enthalpy on the y-axis. Now do remember, because it's exothermic, that our products therefore have less energy than our reactants, which is why it's this way around. We know the arrow is going to go down, and it's by minus 1076 kJ mole to the minus 1. And then just label your reactants. And you can be really precise here because you can actually see what the reactants are. So I'm just going to write C2H4 plus 3O2 as the reactants. And then I can see that the products are 2CO2 plus 2H2O. H2O.
Now we're moving on to rates of reaction. So looking at the effect of temperature, surface area and concentration on rates of reaction. So what effect does increasing the temperature have on the rate of reaction? Well, clearly it's going to increase it. The reason why is because particles have greater kinetic energy, so they collide more frequently. The collisions are harder, and therefore a greater proportion of these collisions result in the required energy to overcome the activation energy. Looking at concentration now. So if you increase the concentration of particles, that means that there are more particles in the same volume. Clearly, collisions will occur more frequently, and therefore the rate of reaction will increase. Surface area now. If you increase the surface area, for example by powdering marble chips, powdered marble chips have a larger surface area than giant lumps, and so by increasing the surface area you're ensuring that you have an increased frequency of collisions, and therefore the rate of reaction will increase. And do make sure you can argue this from if you decrease the surface area, decrease the concentration and decrease the temperature. You just need to say the exact opposite. Remember, there are several ways in which you can measure the rates of reaction. So rates of reaction are given by, for example, a change in volume over time, a change in concentration over time. Now, if we use the marble chip example, remember that marble chips, when reacted with hydrochloric acid, they will produce carbon dioxide. So you can measure how quickly that carbon dioxide is produced, either using a top-pan balance. Now remember, that needs a high resolution because carbon dioxide doesn't weigh very much, so you need at least like 0.00 on your weighing scale in order to measure that difference. So when it escapes out the top of a conical flask, you'll see the mass decreasing, and you can measure that over time. Equally, you could use gas syringes, and that will show you the volume of carbon dioxide that's released. You can't use this method if you're measuring hydrogen gas because it is too light, so you won't actually be able to see a change in the reading on the measuring balance. Sometimes there are experiments involving crosses being obscured due to a precipitate being formed, so you measure the time taken for the cross to disappear, but that's obviously fraught with difficulties because it's very much human judgment as to decide when that cross disappeared. So do be prepared to talk about some limitations related to the methods used. So chemical equilibria now, we are looking at reversible reactions here, so be aware of this special arrow. This is your reversible arrow, and it tells you that the reaction is happening in both the forward and backwards direction, and what that really means is the reactants react to produce the products, as we're used to seeing, but then the products will fall apart effectively and produce the reactants again. So these aren't ideal conditions when we're talking about industrial processes, because it basically means you make very little of the product that you're after, and we use the word yield to describe the amount of product produced. So let's start by looking at what a dynamic equilibrium means. Now, first of all, the word dynamic means that the reactions are ongoing, which means that the forward and reverse reactions are occurring at the same time. Because it's equilibrium, it means they're occurring at the same rate, and that there is no overall change in the concentrations of reactants and products. And this is only true if it occurs within a closed system, and a closed system is simply one where nothing is allowed to escape. So no gases can leave and no more reactants get added. It remains a sealed vessel. So looking closer at dynamic equilibria, let's look at the effect of a catalyst. Now, you must notice that a catalyst simply increases the rate of reaction. We know this, I've just said it. It does it by providing an alternative reaction pathway with lower activation energy. Note, it does not alter the position of equilibrium, so it doesn't increase the yield of the products. It keeps the position of equilibrium in the same place, it just increases both the forward and reverse reactions equally. A summary now of what happens when we choose to alter reaction conditions. So remember, we can alter the position of equilibrium if we change both the temperature and pressure. As I've already said, the catalyst has no effect. Remember, when a reaction is exothermic, the whole reaction gets hotter, and when it is endothermic, the whole reaction gets cooler. So if we start by increasing the temperature, we know we need to oppose the change, so we're going to favour the reaction, which results in a decrease in temperature, which is why increasing the temperature favours the endothermic reaction. And that means that the position of equilibrium will shift to favour that endothermic reaction. So if you have an equation and the delta H says that it is positive, we know that the forward reaction is therefore endothermic. So increasing the temperature will favour the forward reaction. Decreasing the temperature will favour the exothermic reaction, and the position of equilibrium will shift to favour that. And if this is sounding complicated, don't worry, because we're going to use the Haber process as an example to help us understand it. Looking at pressure now, if you increase the pressure, what happens is equilibrium position will shift to favour a decrease in pressure, so it will shift to the side with a fewer moles of gas, and you count the number of moles by looking at the big numbers in front of the formulae. Decreasing the pressure will favour the side with increased number of moles of gas, so position of equilibrium will again shift. So the Haber process, this is the manufacture of ammonia, and it involves the use of nitrogen and hydrogen. Delta H is negative, which means the forward reaction, the reaction which produces ammonia, is exothermic. So in order to increase the yield of ammonia, it makes sense therefore that we decrease the temperature. Why? Because the forward reaction is exothermic, so the position of equilibrium will shift to the right, and therefore more ammonia will be made. However, the problem with low temperatures is it's all to do with collision theory, means that the particles have very little kinetic energy. So although when they collide, a reaction takes place, the likelihood of them colliding is now very low because of the low temperatures, which is why we actually have to increase the temperature to 450 degrees Celsius, and we therefore call these conditions compromised. Looking at the pressure now, if we count the number of moles of gas by looking at the balanced symbol equation, you can see that there are 4 moles of gas on the left-hand side and 2 moles of gas on the right-hand side. So in order to increase the yield of ammonia, we need to increase the pressure, because remember, increased pressure will favour the side with fewer moles of gas. Therefore, the position of equilibrium will shift to the right, meaning that more ammonia is made. Now again, this is a compromised condition, because although the high pressure will favour increased yields, unfortunately high pressures are expensive and they are dangerous because the reaction vessel needs reinforcing, and therefore we used a compromised pressure of 200 atmospheres. We do add an ion catalyst when we're talking about ammonia. The addition of the ion catalyst increases both the forward and reverse rates of reaction, but it has no effect on the position of equilibrium, and therefore it has no effect on the yield of ammonia. Let's look at another example now. So I'm going to bring up an equation which is showing NO2, reversible arrow, and N2O4, and do notice their colours. NO2 is brown and N2O4 is colourless, and look at the delta H sign, it is an exothermic reaction. So let's see what happens when we increase the temperature. So what happens when we increase the temperature is the endothermic reaction will be favoured, which means the reverse reaction will be favoured. So the position of equilibrium shifts to the left. You therefore make more NO2, and so therefore the colour changes and it becomes brown. Looking at pressure now, and we are going to increase the pressure. So let's compare the number of moles of gas on both sides of the equation. You can see that there are 2 NO2s and only 1 N2O4, so increasing the pressure will favour the forward reaction, so the position of equilibrium shifts to the right, and therefore more N2O4 is produced, so the colour will change to colourless. So be prepared to talk about what effect various changes in pressure and temperature will have, and again notice catalysts have no effect. Let's remind ourselves of the definitions of oxidation and reduction. So oil rig, oxidation is the loss of electrons and reduction is the gain of electrons. Redox now, and that, as the name suggests, is a reaction where reduction and oxidation occur at the same time. A reducing agent is a substance which causes another substance to be reduced, so it forces the other substance to gain electrons, and therefore, by definition, a reducing agent is therefore oxidized. An oxidizing agent causes a substance to become oxidized, so it forces the other substance to lose electrons, and therefore, by definition, an oxidizing agent is reduced.
We're looking at rules for determining oxidation states. When we're looking at oxidation states, it all relies on us understanding what oxidation and reduction are. So remember, oil rig will help you with this. So oxidation is the loss of electrons, whereas reduction is the gain of electrons, and that is key. However, at this high level, it's not always easy to see how electrons have been transferred in redox processes, and remember, redox processes are ones where oxidation and reduction occur at the same time. And therefore, oxidation states are a made-up tool made up by us in order to help us identify which species have been oxidized and which have been reduced. And basically, there's a whole set of rules you need to follow. And if you follow those rules, you'll be able to, first of all, work out the various oxidation states, and secondly, work out what has been oxidized and what has been reduced. So to put that into words, oxidation states are a useful tool for allowing us to identify which species has been oxidized and which has been reduced. So here are oxidation state rules, or you could have said our oxidation number rules. It means the same thing. And our first rule you have to learn is that elements which are not combined with other elements have an oxidation state of 0. So let's look at some examples. Oxygen, phosphorus, sulfur as elements by themselves have an oxidation state of 0. For number 2, the oxidation state or oxidation number of any uncombined ion is the same as its charge. So taking sodium ion, for example, its oxidation state will be +1. Calcium, its oxidation state will be +2. So its oxidation state or number is the same as the charge on its ion. Rule 3, the sum of all the oxidation numbers in a molecule is 0. Such as water, carbon dioxide, hydrogen chloride, etc. So the sum of all the oxidation numbers, so that means the individual oxidation numbers here, so the oxidation number of hydrogen and the oxidation number of oxygen, 2 lots of hydrogen plus the oxidation number for oxygen will equal 0. Carbon's oxidation number plus 2 lots of oxygen's oxidation number will also be 0, and so on. NB, linked to this point, we need to consider ions, and we're looking at more complicated ions, so ones which contain 2 or more elements. So I'm going to call that, in a complicated ion, the sum of oxidation numbers is equal to the charge of the ion. So taking the ion SO42-, so the sulfate ion, what that means is if you add the oxidation number of sulfur to 4 lots of oxygen, you'll still have a net charge of 2-. For the nitrate ion, if you add the oxidation number for nitrogen to 3 lots of oxygen, you'll have a net charge of 1-. Next up, a couple of elements which you just have to learn the numbers for. So hydrogen, try and remember that that always has an oxidation number or state of +1. The exception is hydrogen combined as a metal hydride. And here it has an oxidation number of -1. So you must learn that exception. Fluorine is the second element you need to know the oxidation number off by heart, and its oxidation number is always -1. Oxygen now, this is slightly more complicated. It usually has an oxidation number of -2. However, there are a few exceptions. So firstly, in peroxides, it has an oxidation number of -1 instead of -2. And secondly, when it combines with fluorine, it has an oxidation number of +1. In order for this to make more sense, let's write the peroxide formula, and that's H2O2. So hydrogen will have an oxidation state of +1, and oxygen in this case, according to our exception, will be -1. By the way, guys, some teachers might have taught you this in terms of which elements are more electronegative. So you treat covalent compounds as ionic compounds. Obviously that method works too, but this for me is the most straightforward thing to do, because you just have to learn a load of rules and it will make sure you get the answer right every single time. Anyway, rule 7, looking at chlorine now as the element. Remember that it always has an oxidation number of -1. There is an exception here. So when it's combined with fluorine, it switches the sign of its oxidation number to being positive, and the same is true for oxygen. Now, the number it turns into will very much depend on the compound you find it in, and we will look at some examples to make sure that actually makes sense for you guys. And then the last rule, which is fairly straightforward, and hopefully you remember this from GCSE and IGCSE, for groups 1 to 3, the oxidation number is the same as the group number. E.g., sodium is in group 1, so its oxidation number is +1. Now, according to rule 3, the sum of all oxidation numbers in a molecule is 0. We know that overall this charge on the ammonia will be 0. And that's helpful because now we need to work out the various oxidation numbers of both nitrogen and hydrogen. So according to rule 4, we know that hydrogen has an oxidation state of +1. We know that there is no overall charge, so because we have 3 hydrogens, we have a +3 charge. So what must the oxidation number of nitrogen be? Well, it must be -3. Following on from our oxidation state rules, we need to be able to look at redox reactions and look at the equations and decide what has been oxidized and what has been reduced. So we're going to have our rules side by side so we can refer to them, because we'll need to know what the various oxidation states are in order to do these questions. Looking at our first equation, therefore, we've got sodium, which is a solid, oxygen, which is a gas, forming sodium oxide. And we need to compare the various oxidation states of the elements on both sides of the arrow. So starting with sodium, well, according to rule 1, elements not combined with other elements have an oxidation state of 0. So here we know sodium has an oxidation state of 0. Looking at it in sodium oxide, so according to rule 8, for groups 1, 2 and 3, the oxidation number is the same as the group number. So sodium is in group 1, which is why its oxidation number here is +1. Looking at oxygen now oxygen is an element not combined with any other elements. According to rule 1, its oxidation state is therefore 0. And then combined with sodium, so as sodium oxide, we know according to rule 6 that it has an oxidation number of -2. And do check that the overall net charge is 0 on these things to make sure you're doing it right. And now let's just have a look at what's happened with the numbers. So sodium has gone from 0 to +1, which means that it has lost electrons in order to become positive. And because it's lost electrons, according to oil rig, we know that sodium has therefore been oxidized. Oxygen has gone from 0 to -2, which means it's gained electrons, so it has been reduced. And then depending on how they ask the question, you can add a couple more statements. So although sodium has been oxidized, it means it has automatically acted as a reducing agent because it has caused oxygen to be reduced. So you can write sodium has been oxidized, and you can also write sodium acts as a reducing agent. Concurrently, if oxygen has been reduced, it means it's automatically acted as an oxidizing agent. Let's look at a second example where copper oxide reacts with hydrogen to form copper plus water. So starting with oxygen, let's work out its changes in oxidation state. According to rule 6, it has an oxidation state of -2. There are no exceptions here, so we're going to put a -2 here. And looking on the right-hand side, again, oxygen will have an oxidation number of -2. So here nothing's happened to it. It hasn't been oxidized or reduced because its oxidation state has remained the same. Copper now, well, we know the net charge of copper oxide is 0, so by definition copper must therefore have an oxidation state of +2. And then on the right hand side it exists as an uncombined element. According to rule 1, its oxidation state must therefore be 0. Hydrogen now, hydrogen exists as an uncombined element on the left hand side, its oxidation number is therefore 0. On the right hand side, it exists in water, the net charge must be 0. So that means that each hydrogen has an oxidation number of +1. And now we can work out what has been oxidized and what has been reduced. So copper has gone from +2 to 0, which means it has gained electrons in order to become effectively more negative. So copper has been reduced. And we might as well write the matching statement here, which is that it acts as an oxidizing agent. Looking at hydrogen now, hydrogen's gone from 0 to +1. In order to become positive, it must have lost electrons. According to oil rig, it's therefore been oxidized and automatically acts as a reducing agent. Let's look more closely at the topic of acids, bases, and salts. Now, first of all, we need to start by listing the properties of acids. Now, we know an acid donates hydrogen ions. It has a pH of less or equal to 6, because remember pH 7 is neutral. And because of this low pH, remember it turns litmus paper, which is a type of indicator to show how acidic or alkaline a substance is, and that will turn red. Similarly, universal indicator will turn red in a strong acid, orange in a weaker acid like a medium acid, and yellow in a weak acid. You need to be very clear on the reactions, which I'm going to go into in more detail, but just to summarize here, if you have a metal and an acid, you produce a salt and hydrogen. I promise I'll show you examples including actual metals. If you have either a metal oxide or hydroxide plus an acid, you produce a salt plus water. And then lastly, metal carbonates plus acids form a salt plus water, and the carbonate indicates that you'll produce carbon dioxide. The last indicator I meant to mention, which I probably should further up, is to notice methyl orange handily also turns red in the presence of acid. Let's look at bases now. Remember that these are hydrogen ion acceptors. Again, we need an in-depth knowledge of the colour that all the indicators turn. Remember that a base has a pH greater or equal to 8, so they will turn universal indicator blue or purple. Litmus paper again will turn blue. Methyl orange unluckily doesn't turn blue, it turns yellow. Now, in terms of their reactions, you need to remember that a base reacts with an acid to form a salt plus water. And lastly, notice the difference between an alkali and a base. And really, the only difference here is that an alkali is a soluble base. So if we do a little Venn diagram, you'll find that all alkalis are bases, but that not all bases are alkalis. Let's look at the difference between strong and weak acids. The crucial thing here is that in a strong acid, remember it contains lots of hydrogen ions, and what you find is that they readily dissociate. And what that really means in layman's terms, if you have hydrochloric acid, that is a strong acid, and it will extremely easily give up all of its hydrogen ions, or pretty much most of them. Whereas with a weak acid, you find that the hydrogen ions don't readily dissociate. They don't enter the solution easily, and they stay combined with their other ions. So something like ethanoic acid, which is a carboxylic acid, we call this a weak acid because it doesn't give up its hydrogen ions easily. And remember that acids in solution can carry a current, and that's due to the presence of the hydrogen ions. Clearly, with a strong acid, there are more hydrogen ions, so the solution can carry more current than compared with a weak acid. And more easy to understand is the fact that you will see a lower pH with a strong acid, so of approximately 2 maybe, whereas a weaker acid, you'll see a much higher pH of approximately 6. Looking at the bases now, so the strong and weak bases, luckily it's incredibly similar to what we've just learnt with the acids. So you can pretty much say the same thing, which is that a strong base will readily dissociate. A weak base will not readily dissociate. Again, similarly, you'll see that you can carry a much larger current with a strong base. And in terms of the pH, you're looking at about a pH of 13 for a strong base, whereas a pH of around 8 will be seen with a weak base. So we've talked a lot about pHs. Let's quickly chat about it more. So the pH of 7, as I've already said, is neutral. pH of 14, which is one end of the pH scale, will be very strong alkali or base. A pH of 0 will be a very strong acid. And then you have the intermediate value, so pH 8 will be a weak alkali or base. A pH of 6 will be a weak acid. And let's look at the colours. So neutral is green. You get quite purpley at the very strong alkali end, and you get red at the acid end. And we like universal indicator because that can basically show you what pH you have. You add the universal indicator to the solution, it turns a certain colour which you can compare to a scale and work out the approximate pH.
We're now going to cover the salts topic, and when we're talking about salts we need to know a lot about acids and bases because that's where the salt originates from. So do remember your definition of an acid, which is that it is a H+ donor. A base is a H+ acceptor, and it also tends to be a hydroxide donor. And examples of bases include metal carbonates, metal hydroxides and metal oxides. Just remember the difference between a base and an alkali. They're very similar. An alkali is simply a soluble base. So remember, all alkalis are bases, but not all bases are alkalis. So some background about salts. So effectively, a salt is formed when the hydrogen of an acid is replaced with either metal or ammonium. For example, say you had hydrochloric acid, you acted it with potassium oxide, then you would end up with potassium chloride, which is the salt. Taking sulfuric acid now, pretend we reacted it with calcium carbonate, you'd end up with calcium sulfate, which is the salt. So now let's look at some common acids and the salts that they produce. Now in terms of the reactivity of acids, remember that only metals above hydrogen in the reactivity series will react with acids. So things like copper, silver and gold, which lie beneath hydrogen in the reactivity series, will not react. Elements at the very top of the reactivity series, such as potassium, sodium and lithium, they will react extremely explosively, and I don't recommend that anyone tries this because it would be extremely dangerous. So now let's take you through the salt equations. So we're going to start with looking at the general equation. When you have metal plus an acid, that forms salt plus hydrogen, and I'm going to show you some examples. If you have metal oxide plus an acid, then you make salt and water. Metal hydroxide this time, it's the same as metal oxide in that you produce a salt and water. And lastly, metal carbonates, when you react those with acids, you produce a salt plus water, and then because of the carbonate, you produce carbon dioxide. So do make sure that whatever is on the product side started off on the reactant side. Don't start creating carbon dioxide on the right-hand side when there was no carbon on the left-hand side. And similarly, don't have hydrogen and water forming on the right-hand side. Only one of them forms, so make sure you know which one it is. So solubility rules, learning which salts are soluble and which are insoluble. The reason why I'm smiling is because this is disgusting. It's awful, I really struggle to remember them. Now there is a huge table which you can try and learn off by heart, but I much prefer to learn the rules, and if you assume that most things are soluble and learn the exceptions, that's a good way to go. So let's start by stating that all nitrates are soluble. All potassium, ammonium and sodium compounds are soluble. All sulfates are soluble. There are 3 exceptions, and that is lead-2, calcium and barium sulfate. All chlorides are soluble except from lead-2 chloride and silver chloride. Now we switch and we look at things which are insoluble. So we say that all carbonates are insoluble. The exceptions will clearly be the sodium, potassium and ammonium compounds, which makes sense because I've already told you that the sodium, ammonium and potassium compounds are soluble. And similarly, all hydroxides are insoluble, the exception being sodium, potassium and ammonium compounds. So let's just do a quick test on that. So I'm just going to say a couple of salts and you need to decide if they're insoluble or soluble. So starting with lead nitrate, That is soluble because it contains nitrates. Next up, potassium carbonate. That is also soluble because it contains potassium. Now we're looking at magnesium sulfate. That is soluble because remember all sulfates are soluble with a few exceptions. What about barium sulfate? Well, that was one of the exceptions you had to learn, so that is insoluble. And now calcium carbonate. That is insoluble because it is carbonate and it is not sodium, potassium or ammonium. So I hope you can see you can work it out using these rules. So let's look at the different methods for making these salts, and we're going to start by looking at soluble salts, but do notice these are ones which do not contain ammonium, potassium or sodium. So what you can do here is you can use metal oxide, a metal hydroxide or metal carbonate. You react it with the acid and you form your soluble salt. You can also use metals plus acid, so it doesn't need to be combined with an oxide, hydroxide or carbonate, but do notice that you need a metal which isn't mega reactive, because clearly if you're reacting it with an acid you could end up with a dangerous explosion if you're using group 1 metals, so be sensible and use something like magnesium. Now the method you're going to actually use is crystallization. Your summary for this is that you're going to react, for example, your metal hydroxide with your acid. You're going to filter in order to remove any undissolved solid. Then you're going to evaporate, so you're going to place that solution in an evaporating basin over a Bunsen burner with gauze and a tripod, and you're going to get rid of excess water, so you'll evaporate some of the water. Then you're going to allow the mixture to cool, and eventually you want to let it dry out in a warm place, so on a warm windowsill, in a drying oven for example, or on paper. Looking at making soluble salts now, ones which do contain sodium, potassium or ammonia, you're going to use a slightly different method. Now the reason why you can't use the crystallization method I just described, because the sodium, potassium, ammonium are extremely soluble. So if you added them to acid, which contains water, they would react with both the acid and the water and they would continuously dissolve away, meaning that there'd be nothing to filter and therefore nothing to evaporate. So that's why crystallization doesn't work in this case. So in this situation you have to use the titration method. So titration is the method you use when making ammonium, sodium or potassium salts. The reason you use the titration is because you need to know the exact volumes of acid and alkali you need to add in order to make the salt. So for example, we set up our burette and it contains the acid. We place the alkali in the conical flask together with an indicator, and then as you know with the titration you keep adding the contents of the burette to the conical flask, swirling all the time until you get that indicator to change. And when it does that, you know you have the exact volume of acid and alkali. Then you repeat the entire experiment, this time without the indicator, because obviously that would disrupt your salt. And because you know the exact volumes of both the acid and the alkali, you can create the exact amount of salt. There won't be any excess to dissolve away, and therefore you'll have a perfect salt. Once you've done that, your method is the same as we've just described with crystallization. Because you've got your solution, you now need to evaporate off the excess water. You need to allow it to cool, and then you're going to leave it to dry in a warm place again. So it's very similar to the crystallization method. You still use it, but unfortunately you have to use the titration method initially in order to obtain the correct volumes. Lastly, we're making insoluble salts. In this case, you're going to react 2 soluble salts, and obviously make sure you pick the right salts that will create the insoluble salt you're after. So if you're after barium sulfate as your insoluble salt, clearly the first thing you're reacting has to contain barium, so something like barium nitrate. The second thing has to contain sulfate, so it could, for example, be potassium sulfate. You react them together in order to form barium sulfate, and left over will be potassium nitrate. So do be sensible, make sure that whatever's going in will make your insoluble salt, which is why it's important that you know your solubility rules, so you know which salts are soluble and which ones are insoluble. By the way, this is a disgusting topic, everyone thinks so don't worry if you're finding it quite tricky. So when you're making insoluble salts, this is actually the most straightforward method you'll use. You're going to react, so you're going to mix those 2 soluble salts together. You're going to filter to remove any excess solid. You're going to wash, again to remove that excess solid. And lastly, leave to dry, and do state where you're drying it, don't just say dry, so say in a warm place or on filter paper or in an oven. And this method we describe as being the precipitation method. I'm just going to describe an example of the precipitation method to try and show you exactly what is going on. So in this example, we're going to take silver nitrate and sodium chloride. Notice that they are both soluble because they contain nitrate and they contain sodium. So what happens when you place them in solution is all the ions separate, so you're left with Ag+, which is silver, chloride ions, which is Cl-, nitrate ions, which are NO3-, and sodium, which is Na+. Now, in order to make that insoluble salt, remember what we want to happen is for the silver and the chloride to be attracted, and indeed they are strongly attracted, forming silver chloride, which is an insoluble salt. Now the remaining ions, the nitrate and the sodium, are very weakly attracted, so they remain in solution, and they're the soluble salt formed. Group 1 elements now, so remember that is the first column of the periodic table. It is the alkali metals. They all have the same chemical properties because they have one electron in their outer shell. Now remember, as you descend that group, the elements become more reactive. They're all extremely reactive as it is, but as you descend the group they get more reactive. The reason for this is because as you descend the group, the atoms get larger, because if you actually look at their atomic number, it's higher for potassium compared with lithium, so the atoms are larger. This means the outer shell electron is further from the nucleus, which means that it's more shielded by the inner shells of electrons. This means it's easier to lose the electron, and remember, when we lose the electron, that's when it partakes in chemical reactions, so it's more likely to do that, so it is more reactive than elements higher up than it in the periodic table. I've already touched on the fact that group 1 metals are extremely reactive. This means that they must be stored in oil because they'll react with the slightest bit of moisture. They're soft and you can actually cut them with a knife, and they oxidize very easily, so they go from being shiny to oxidized very quickly on exposure to air. Other properties they have is they have low melting and boiling points, which makes them quite unusual for metals, and they also have a low density, and we can see this when they're placed in water. They actually float on the water, so again these are really quite unusual properties for the group 1 metals. Now they're very reactive, as I've already said, and they can react with oxygen to form oxides, so potassium oxide for example. They can react with cold water to form hydroxides, potassium hydroxide for example. They can react with the halogens. Remember, those are the elements in group 7 of the periodic table, to form something like potassium chloride, and they can partake in ionic bonding. Let's now look more closely at observations when they're added to water. So this will be true for all group 1 elements. First of all, they fizz, and what that actually means is they're releasing hydrogen gas. They float, they move around, they form a small ball which eventually dissolves. If you were to add universal indicator to that leftover solution, you would see that it would turn blue, and that makes sense because remember, blue indicates alkali and they're called the alkali metals, so that makes perfect sense. In terms of more specific observations, remember that lithium doesn't produce a flame. However, sodium produces an orange flame when added to water, and potassium produces a lovely lilac flame. Learn the word equations for when they're added to cold water. So I've already touched on this, but a group 1 metal plus cold water will produce a metal hydroxide plus hydrogen, which makes sense due to the fizzing that you witness. So taking lithium, for example, plus water forms lithium hydroxide and hydrogen. We don't add them to steam or to acid because that would be incredibly dangerous. They also burn in air and they produce very characteristic flame colours. So lithium burns to form a red flame, a crimson flame. Potassium again produces a lilac flame, and sodium produces a yellow flame. In terms of making predictions about group 1 metals below potassium, so things like francium. Now you don't need to learn these observations off by heart, but do notice that these observations with water will be more violent because obviously, for all the reasons we've already described, the atoms are larger, more shells of electrons, the electron further from the nucleus. So just be prepared to talk about the fact that they'll be more violent, but you'd still see the same set of observations: fizzing, for example, a flame, moving around, floating, melting, etc. Right, so the halogens, we're looking at group 7, so these are the elements including fluorine, chlorine, bromine and iodine. Now don't forget their states at room temperature. Fluorine and chlorine are gases at room temperature. Fluorine is a yellow gas, chlorine is a green gas. Then you have bromine, which is a red-brown liquid, and finally iodine is a grey solid. Don't forget, iodine undergoes a process called sublimation, which is when it turns directly from a solid to a gas, and in the case of iodine it goes from a grey solid to a purple vapour. Now the halogens react with hydrogen to form hydrogen halides. For example, hydrogen plus bromine forms hydrogen bromide. These are very acidic and poisonous, and they're also very soluble in water. So something like HCl gas will turn readily into hydrochloric acid, so that's HCl aqueous on addition with water. You need to know about halogen displacement reactions, because more reactive halogens will displace less reactive halogens from their compounds. Let's quickly look at the reactivity of the halogens. So remember, at the top of the group, that's where they're most reactive. Towards the bottom, they're at their least reactive, and we can look at the reason for this. So iodine is much less reactive than fluorine because iodine is much larger, so it has far more shells of electrons. This means that the outer shell electrons are farther away from the nucleus, they're more shielded, and because of that it's harder to gain that extra electron in order to become full, hence they are less reactive, and this helps to explain why iodine is solid at room temperature. So if we look at the halogen displacement table, we tend to only look at the elements chlorine, bromine and iodine. You'll find that chlorine displaces both iodine and bromine from their compounds. You clearly don't react chlorine with itself, so potassium chloride, because there'll be no reaction. If you try and displace a potassium chloride, for example, using iodine, that won't happen because iodine is less reactive. So just learn the rules for this and the summary equations. In terms of their general properties, remember they have low boiling points and low melting points, and they are poor conductors of heat and electricity. So metals now, we're going to start by looking at their properties. So remember, metals have high melting and boiling points, they're good conductors of heat and electricity, they are shiny, they are sonorous, which means when you hit it they make a noise, they are malleable and ductile. So what does malleable and ductile mean? Well, malleable means that they can be hammered into shape, and ductile means they can be drawn into a wire. Another thing to notice is stuff relating to how they bond. So be aware that when they enter into bonding, they tend to lose electrons to become positive ions. They form basic oxides, which we'll come into later, and they partake in ionic bonding. Non-metals now, their properties include the following. They are dull, so they're not shiny. They tend to have low boiling and melting points. There are exceptions to this, which we'll come on to later, but that is the general rule. They are brittle, which means when you hit them they easily break. They form acidic oxides, they gain electrons in bonding to become negative ions, and they partake in covalent and ionic bonding. Why do we go to such effort to obtain aluminium? Well, it's because it's an extremely useful metal. It has really great properties, mainly because it has low density. So compared with other metals, it's light, but we can't say light in the exam, we say low density, which means it's good for use in making aeroplanes. We've obviously also seen its use in making drinks cans, etc. It's also a really good conductor of heat, which is why you find a lot of pans are made out of aluminium, which is why wiring can sometimes be made out of aluminium.
Now copper. Copper is commonly used in electrical wiring, and that's because it's an excellent conductor of electricity. Coupled with that is its ability to conduct heat, which means it can be used to produce cooking pots and pans, so saucepans.
And touching a bit more on this, why do alloys tend to be harder than pure metals? Remember, an alloy is a mixture of metals, or something like a mixture of metals and a non-metal. So for example, steel is an alloy of iron because it contains iron and carbon. Now, why do alloys tend to be harder than pure metals? That's because the alloys have ions of different sizes, which means the layers can't slide as easily, so it's not as easy to distort the layers. looking at the uses of iron, and you need to know about the different types of iron in terms of how much carbon they contain. Don't forget that when iron has carbon combined with it, it's now formed an alloy, and that alloy is called steel. So looking at low carbon steel, so that's steel containing less than 0.25% carbon, you find that this steel is very strong, malleable and ductile. Don't forget, malleable means it can be hammered into shape, ductile means it can be drawn into a wire, and its use is in car bodies, so that's to make the outside of a car, for making bridges and shipbuilding. There are disadvantages with using low carbon steel, and that's because it rusts easily and it's very heavy due to its high density. Stainless steel, this is an alloy containing also chromium, nickel, and obviously iron. This is highly resistant to corrosion or rusting, which means it makes great cutlery. So a lot of your cutlery, your knives and forks and spoons will be made out of stainless steel, and you'll probably see it written on there. It's also used to make saucepans and gardening tools. The reactivity series. So you need to learn the order of metals in the reactivity series, and that is potassium, sodium, lithium, calcium, magnesium, aluminium. Then we mention carbon because although it isn't a metal, it's good to use it as a reference point. This is followed by zinc and then iron. Hydrogen comes next, not a metal, but still a good reference point. And lastly, our unreactive metals go copper, silver, and then lastly, the most unreactive is gold. And that explains why you find silver and gold native in the Earth's crust. You can literally just find it in streams and rivers, and that's because it's incredibly unreactive. Even though aluminium looks fairly reactive because it appears quite high in the reactivity series, due to its oxide layer, it means it's less reactive than you would imagine. So we have an unknown metal and we don't know how reactive it is. So there are several things we can do to try and determine its position in the reactivity series. So first of all, we would try to react it with cold water. Now only very reactive metals, such as those found in group 1, so we're looking at potassium, sodium and lithium for example, will react with cold water, and they'll form metal hydroxide plus hydrogen, which we've already met. If they don't react with cold water, you can then try steam, and this will produce a metal oxide and hydrogen. And then lastly, if it doesn't react with steam, you can try acid, and that will produce a salt plus hydrogen. And you obviously wouldn't try reacting group 1 metals with acids because they are far too reactive. Do notice that when you look at the reactivity series, only elements which are more reactive than hydrogen will react with acids, and that's because acids contain hydrogen, such as hydrochloric acid, it's HCl, sulfuric acid, H2SO4, nitric acid, HNO3. So in order to react with acids, they must be more reactive than hydrogen. Looking at protecting iron from rusting. So rusting is when metals flake away, and you only use the word rust when you're talking about iron. If you talk about any other metal, you can't call it rust, you have to say it corrodes. So you could say that zinc corrodes, but only iron rusts. So what conditions are needed for rusting to occur? You need water and oxygen for this, and salt actually increases the rusting process but is not necessary. What are the different ways in which we can prevent rusting? There are the simplest ways, which is just simply painting or using oil and grease to protect the iron and stop it being exposed to water and oxygen, or you can become more fancy and use methods such as galvanizing. So galvanizing is when you use a more reactive metal such as zinc, and it reacts before the iron. And so actually what happens is the zinc ions and donates electrons, and what that means is the electrons can flow to iron, and therefore if the iron starts to rust and form ions, this is hard, why have they got the same name? Those electrons which have been donated from zinc can help the iron form its iron atoms again so it doesn't rust away. Try not to worry too much if you're not understanding what I'm saying. Just learn that galvanizing is using a more reactive metal to protect iron. When other metals oxidize and react in preference to the iron through the method of galvanizing, don't forget we call this sacrificial protection.
Now we know that metals are incredibly useful. They're used as all sorts of building materials in everyday life, such as aluminium drinks cans, but we need to know how we can extract them, and there are two main methods, which is either heating with carbon or electrolysis. And the method you use very much depends on the reactivity of the metal, because you can only use the heating with carbon method if your metal is less reactive than carbon. For metals which are more reactive than carbon, heating with carbon will have no effect, and therefore you have to use electrolysis, which is far from ideal because electrolysis is an incredibly expensive process as it involves the use of electricity. For extremely unreactive metals such as gold and silver, you find these native, so not reacted with oxygen or anything. They're not found as oxides, they're literally found as gold and silver, native in the Earth's crust, which is why people used to pan for gold in rivers in America about 100 years ago in order to find the gold sitting in the riverbed. So let's look at the blast furnace, which is all to do with purifying iron. And that iron exists as iron oxide in the Earth's crust, which we call hematite. Remember that heme means related to iron in the way that hemoglobin, found in red blood cells, contains iron. So try to remember that. Now, we're going to use the heating with carbon method. And the reason we can do this is because carbon is more reactive than iron. So this is a good process because it's not incredibly expensive. So let's start by looking at the raw materials which will enter our blast furnace. These are obviously the carbon, which is entering in the form of coke, the iron oxide, and it's iron 3 oxide, and lastly limestone is added to remove acidic impurities. And now it's essential that we look at the various equations involved in the blast furnace. So our first step is reacting carbon, so the coke, with oxygen to form carbon dioxide. And if they ask you, the point of this reaction is to produce the heat needed. Next up, we're going to react that carbon dioxide produced in that step with carbon to produce carbon monoxide, and do make sure you balance the equation. And remember, this is going to be the reducing agent, which is all important as that actually is going to remove the oxygen from the iron oxide. The next important step is what we're really after, which is purifying that iron. And it's going to produce iron by itself and carbon dioxide. Let's do some balancing. And our summary here is that iron oxide is reduced to iron. Now it's important that we look at the limestone step. So this is kind of separate to everything that's gone on before. So we have our calcium carbonate, which is obviously limestone. It's going to undergo a thermal decomposition reaction, so make sure you can name the type of reaction, to produce calcium oxide and carbon dioxide. And it's that calcium oxide that's important because it reacts with the acidic impurities found within the blast furnace, producing calcium silicate, which we remember the formula of, because remember most people have a calculator which is of the brand Casio. And if you remember that it's Casio 3 and making sure that you lower and uppercase the appropriate letters, you can therefore remember calcium silicate's formula, and its colloquial name is slag, which is a very strange name, but that floats on top of the iron. And that is a summary of the blast furnace. Remember, this final reaction here is a neutralization reaction.
When you now look at aluminium, because that's another useful metal, that's also too reactive to be found by itself in the Earth's crust, so it's found combined with oxygen. You can't use the blast furnace in order to obtain the aluminium because aluminium is more reactive than carbon. So if you try and burn them together, nothing happens. So this is where electrolysis comes in, and we use aluminium oxide, we electrolyse it, and we have to therefore use huge amounts of electricity, and that's why it's a far more expensive process compared with iron's blast furnace. The second real expense with aluminium is, if we look more closely at the reaction taking place, what you find is there are carbon anodes which dip into the solution containing aluminium oxide. Because they're anodes, clearly they will be positively charged. This means that they attract the oxygen, which is the negative ion. And if we look at the summary equation, we can see that O2-, which is the oxygen ion, loses electrons, so it's oxidized to become oxygen gas. But the oxygen gas formed actually reacts with the carbon electrodes, forming carbon dioxide, which actually burns away the electrode. So in a month or so's time, the whole electrode disappears effectively, so it needs replacing really regularly, which is why it's such an expensive process. We might as well talk about the reaction occurring at the cathode. So remember, that is the negative electrode. So here the aluminium ion will be discharged. So aluminium, Ar3+, it will be reduced because it has to gain electrons in order to become Al. So it gains 3 electrons, which is why we say reduction has taken place. And have another look at the electrolysis part of this video if you're unclear as to what I'm saying. Now we need to look at the chemical and physical tests for water. So the physical test for water is you just need to check a substance's boiling point. If it boils at 100 degrees Celsius, you know you have water. And linked with this, how do you show that water is pure? Well, I've already talked about pure substances having one distinct boiling point, and the same is the case with pure water. The whole lot should boil at 100 degrees. If it's boiling over a range, it tells you it's not pure. Now, using a chemical test for water, you want to add white anhydrous copper sulfate. Anhydrous means lacking in water. Once it's exposed to water, it should turn blue, and that tells you that the substance you have is water.
How do we make potable water or water suitable for drinking? So first of all, we want to find a clean source of water. So ideally not one that's full of pathogens, so bacteria and dirt. And then after this, we do need to make sure we clean it a little bit. So we use a screen to trap any large particles. A coagulant is added, and a coagulant is a substance which causes particles to stick together. Next up, flotation tanks. Make these particles float so they can be removed. They're literally skimmed off the top. Then we filter to remove smaller particles. Add chlorine, because chlorine, remember, it's a halogen, it's incredibly toxic, so that helps to kill the pathogens. But obviously we don't want to add too much chlorine because then it would be unsafe for us to drink. And then lastly, that water needs to be stored in a clean environment. Let's look at fertilisers now. So remember, we add these to our fields to help the crops grow a little better. So what elements do fertilisers contain? Well, firstly, they contain lots and lots of nitrogen. And nitrogen is essential because it is needed by plants to produce amino acids and proteins. Fertilisers also tend to contain a lot of phosphorus, which is needed in the healthy growing of roots and to help crops ripen. And then lastly, potassium. Now notice that lots of fertilisers are called NPK fertilisers, and we can see that the N stands for nitrogen, P stands for phosphorus, and K stands for potassium as per their symbols in the periodic table. We're going back to potassium. Why is this needed by plants? Because they use it to produce proteins and to help them resist diseases. So first up, air is largely nitrogen gas, and 78% of it is nitrogen. Remember, nitrogen is a diatomic gas, which is why we write N2. 21% is that life-giving gas oxygen. Again, it's diatomic, so we write O2. And then we have much smaller amounts of carbon dioxide, so CO2. Little bits of water vapour, as well as group 0, so noble gases, so less than 1%. Now we're going to touch on various pollutants, starting with carbon dioxide, carbon monoxide, methane, oxides of nitrogen, and sulfur dioxide. Now you need to know where these various pollutants come from. So carbon dioxide is produced by the complete combustion of fuels. So what does that mean? It's when you burn fuels in a plentiful supply of oxygen. Now carbon monoxide, if we just quickly look at the difference in their formulae, carbon dioxide is CO2, carbon monoxide is just CO, so it contains one oxygen, and that's because it's produced by the incomplete combustion of fuels. And that means that there was insufficient oxygen in the engine. Methane, CH4, comes from the decomposition of vegetation and the waste gases from the digestion of animals, and that's how it's worded in your specification. You'll probably more commonly have known it from biology, so that would be the rice paddy fields in terms of decomposition of vegetation, and it would be cattle farming in terms of waste gases from digestion animals. When the cattle burp and fart, they release methane. Now the oxides of nitrogen, I've just changed colour so you can see easily where I'm writing. They're produced due to the high temperatures in car engines cause the oxygen and nitrogen, which we've already said are present in air, to react together. And then sulfur dioxide, well, the sulfur comes from sulfur impurities, which are originally in the crude oil used to produce the fuel. So that's where these various pollutants originate from. Now we need to look at the adverse effect that they actually have. So carbon dioxide, again, you may have studied this in either biology or geography. It's a greenhouse gas, which in larger amounts can cause global warming. And we know that that leads to massive amounts of climate change and extinction of species. Carbon monoxide is a toxic gas. Why? Because it combines irreversibly with red blood cells in the blood and therefore lowers oxygen carrying capacity of the blood. Methane is a greenhouse gas, so everything we've written over here relating to carbon dioxide is again applicable for methane. Now, oxides of nitrogen lead to acid rain because those nitrogen oxides dissolve in rainwater to form acid rain with low pH. They can cause photochemical smog and respiratory problems. And then sulfur dioxide is another form of acid rain. One final thing to mention is particulates, which again tend to be caused by unclean fuel. These lead to increased respiratory problems and also increased cancers. Now, if you're doing the extended paper, you need to know quite a lot of detail to do with the greenhouse effect, and so we're going to use this diagram to help us. So the first thing to be aware of is the sun over here emits thermal energy in the form of infrared radiation, and that's going to enter the Earth's atmosphere. Now, some of this thermal energy is absorbed by the Earth, but then you find that some of it is reflected back out into space. And if we look more closely at that absorption of the thermal energy, how's that actually carried out? It's carried out by greenhouse gases such as carbon dioxide and methane, and this is perfectly normal. However, due to all the human activities we carry out, such as burning fossil fuels, deforestation, you find that as those levels of greenhouse gases in the atmosphere rise, more thermal energy is absorbed and trapped. So human activities, e.g. deforestation, and combustion lead to increased greenhouse gases, meaning that more thermal energy is absorbed and trapped. So our Earth's average temperature is rising. This is known as the enhanced greenhouse effect. Less thermal energy is lost to space, and therefore global warming has taken place. Now, we're always looking at ways in which we can reduce the effects of these environmental issues. So how do we reduce the effects of human activity on the Earth? So to reduce climate change, we can do quite a few different things. We can plant more trees, because remember, carbon dioxide is used by trees in their photosynthesis. And then a useful byproduct of photosynthesis, remember, is oxygen, which we need for respiration. We can decrease our livestock farming. Make the links here. Why? Because fewer cows means a reduction in methane gas, which is burped and farted out. We can decrease our use of fossil fuels, so less complete combustion will lead to less CO2 being released. Less incomplete combustion will lead to less carbon monoxide being released. And remember, linked with fossil fuels was also nitrogen oxides and sulfur oxides, which lead to acid rain. So if we burn less fossil fuels, then theoretically we'll have less acid rain. And then what active things can we do? Well, we can use hydrogen as a fuel, because remember that produces water as a waste product, which is perfectly fine, not at all bad for the environment or ourselves. And because of that reason, it's a clean fuel, so no CO2 or carbon monoxide is produced. We could also use renewable energies for the same reason, fewer polluting gases produced. And what kind of renewable energies? So touching lots on geography, biology and physics here. Solar, wind, tidal, to name 3. Now we're going to touch more on the acid rain points. So how are we going to reduce acid rain? Through use of catalytic converters. We're going to reduce our emissions of sulfur dioxide, use low sulfur fuels, and then we're going to carry out flue gas desulfurization with calcium oxide. So flue gas is just waste gases that come from combusting any fuels. So we're saying that we're going to remove the sulfur, so desulfurization of those waste gases, and the substance we're going to use that is calcium oxide. Now we're going to look at slightly more detail as to how that catalytic converter works. Notice that the gases going into the catalytic converter are produced carbon monoxide by the incomplete combustion of fuels, nitrogen oxides due to the high temperatures found in car engines, oxygen obviously is fine. Then you have a honeycomb structure which increases the surface area. The honeycomb actually contains metals such as platinum, and that platinum is acting as a catalyst, and what you actually find is the carbon monoxide is converted to carbon dioxide. Yes, it's still a greenhouse gas, but at least it's not toxic anymore. That nitrogen oxides which cause acid rain are converted to nitrogen gas, Lyra, and then oxygen remains unchanged. You take that carbon monoxide going in as well as the nitrogen oxides, and they are turned into carbon dioxide and nitrogen gas, and then finally don't forget to balance it. And so that's your summary equation. Strangely, we do need to mention photosynthesis at this point, which if you're studying biology you'll be very familiar with. Remember, that's a reaction carried out by plants, and it's used to produce their food, glucose. In terms of the equation for this reaction, you need carbon dioxide, water, light energy, and that's going to produce the plant's food, glucose, and then oxygen as a byproduct. Remember that this takes place in plant cells. So if we draw a basic plant cell here, we have the nucleus, cell wall, cell membrane, vacuole, cytoplasm, and in terms of where that photosynthesis is carried out, it's in the all-important chloroplasts, because they contain a photosynthetic pigment known as chlorophyll. Now, for anyone studying extended science, you'll need to learn the balanced symbol equation. So carbon dioxide is CO2, water is H2O, glucose is C6H12O6, oxygen O2, and then just remember you need to add a 6 in front of everything apart from glucose, and you'll have your balanced symbol equation.
So let's look at organic chemistry, one of my favourite topics. So first of all, organic chemistry, what are we talking about? We're talking about hydrocarbons. So what is a hydrocarbon? It's a compound containing hydrogen and carbon only. Make sure you say only in order to get that second mark. So when we're looking at organic chemistry, we're really looking at different families of compounds, and the simplest family is the alkanes. And I'm going to show you now how to draw out the first 4 alkanes, and we'll have a look at their general formula.
Let's look at how we're going to draw various families of compounds, starting with the simplest, which is the alkane family. Do notice their general formula is CnH2n plus 2, and you must obey that when you're working out the molecular formula. If we take C4H10 as an example, this is a molecular formula because it shows the actual atoms of each element present in the compound. So it shows that this particular compound has 4 carbon atoms and 10 hydrogens. To make it into an empirical formula, just cancel down those numbers. So it becomes C2H5, because you can obviously divide 4 and 10 both by 2. This is therefore the empirical formula because it shows the actual atoms of each element present in a compound. And then just to notice, a displayed formula is when you draw out all the bonds, so something like that. So let's start by working out the first alkane. So obviously it's going to have 1 carbon atom. According to the general formula CnH2n plus 2, so substitute in the number of carbon atoms as n, so it becomes C1, and then 2 times 1 is 2, plus 2 is 4, so H4. Because it looks a bit strange to write the 1, I'm just going to erase that. There's an invisible one, so it's CH4. Its displayed formula looks like this, which is you draw the carbon in the middle and hydrogens around the outside, remembering that each carbon atom forms 4 bonds, each hydrogen forms 1 bond, and you must remember that to help you draw them. Its name, well, it contains 1 carbon, which is why it's meth, and it's an alkane, which is why it's methane. So looking at the second one this time, 2 carbons, so we're going to have C2, and then according to the general formula, 2 times 2 is 4, plus 2 is 6, so its molecular formula is C2H6. Drawing it out, therefore, carbons in the middle, then you've got your hydrogens filling up around the edge, each having 1 bond, and each carbon atom has 4. Because it's still an alkane, it ends in ane, but it contains 2 carbons, which is why it's ethane. The third one now, so it's C3, 2 times 3 is 6, plus 2 is 8, H8, 3 carbons in a line, ends in ane, it contains 3 carbons, so it's propane. For 4 carbons I ran out of space, so it will be C4H10, and it contains 4 carbons, which is why it's bute, still an alkane, so butane.
So these are the simplest hydrocarbons, and we call them saturated, and that's because all the carbon bonds are single. If we look at alkenes, they are unsaturated, and that means they contain a double carbon bond. I'm going to show you how to draw the first 4 alkenes.
Let's now look at the alkenes, and remember they have a general formula which is CnH2n. Let's first of all start by discussing the functional group of the alkenes. Remember, this is the series of atoms or bonds which makes a particular family of compounds special. So here we see that the alkenes contain a C double bond C. By definition, therefore, they need a minimum of 2 carbon atoms to exist, which is why one carbon alkene does not exist. And we have to start with the 2 carbon. So starting with the 2 carbon one, we know we need to substitute 2 in as the n, so it becomes C2 and then simply H4. The displayed formula, we need a double bond, and therefore we're going to fill up our hydrogens. Do notice again that the carbons have 4 bonds, the hydrogen has 1, contains 2 carbon atoms, which is why it begins with eth. It's an alkene, so it's ethene. Looking at 3 carbon atoms now, so C3H6. Again, make sure you're filling these up properly, double checking the bonds. I can't reiterate this enough. And this will be 3 carbons, so prop, it's an alkene, so propene. Now looking at the 4 carbons, which is when it gets a bit more interesting. So we've got C4H8, and therefore we can draw the first version of this like this. In terms of its name, it's butene. However, we now need to look at the other available isomer. Remember then, isomer is something with the same molecular formula but different structural formula. So if we draw that molecular formula out again, C4H8, but we try and work out a different structural formula, we can simply shift that double bond along so it now appears in the middle, and now just fill in those hydrogens. making sure you don't draw too many bonds on those central carbons. And you can see this is still C4H8, however the structures are different, and therefore these are both isomers, and the way in which we name them is according to where you find that double bond. Because the double bond in the black version is between the first and second carbon, we call it but-1-ene. Because the double bond is between the second and third carbon atom, we call this but-2-ene.
Now, these families of compounds we call homologous series, and that's just a fancy way of describing a family of compounds. So what can we say that all members of the same homologous series have in common? So what do all alkanes have in common? What do all alkenes have in common? Well, first of all, they have the same chemical properties, which makes sense. They're going to react in a similar way because they have the same functional group. They're therefore going to have the same functional group, which is good because I just said that. They obey the same general formula. So all alkanes, for example, will follow CnH2n plus 2, whereas all alkenes will obey CnH2n. And then they show a trend or a gradual change in physical properties, which again makes sense. So ethane has 2 carbon atoms, whereas methane has 1. So therefore you'd expect ethane to have a higher melting point and boiling point, which it does. So what is a functional group? Well, it is an atom or a group of atoms which determine the chemical properties of a compound. So we talked about alkanes and alkenes, but where do they all come from? And they come from crude oil, which is a black sticky substance which comes out of the Earth's crust, and it has made some people billionaires because this stuff is worth a lot. Why? Because once it has been sorted, once it has gone through fractional distillation and been separated out into various fuels, that can be sold for a huge amount of money. Why? Because fuels are essential for how we run our lives, it's how we heat our homes and how we run our cars. So what is a fuel? Well, it's a substance which releases energy when burnt. We've talked about crude oil, but how is fractional distillation actually carried out? So we get our crude oil, which we know is a mixture of hydrocarbons, we heat it until it evaporates, and then we pass that vapour into a fractionating column or tower. Now that fractionating column has a temperature gradient, which means it's hotter at the bottom and cooler at the top. So in terms of these various crude oil fractions, and a fraction is just a group of compounds with similar boiling points, they will condense at different positions within the fractionating tower. So the longer chains will condense at the bottom where it is hottest.
So looking at fractional distillation, so we're looking within the fractionating column and we need to know the different fractions starting from the top and various uses. So refinery gases, this is bottled gas used in central heating and cooking, so within our homes basically. The next fraction down we have petrol, otherwise known as gasoline, and as the name suggests, it's used as fuel for cars. Getting slightly longer in terms of our carbon chain, we have naphtha. Its main use is to produce chemicals. Then we have paraffin, which is used as jet fuel. Diesel oil now. This is a heavier fuel and it tends to be used in lorries and buses. Getting longer again with our carbon chain, we have fuel oil, which is fuel for ships. And we also produce lubricants, which are slippery and therefore used in waxes and polishes. And then the last fraction is bitumen. It's black and sticky and we can use it in road surfacing.
A couple of words to be aware of. First of all, viscosity. So that's how readily a fluid flows. Be aware that the more viscous a fluid is, the less readily it flows. So honey is very viscous because it's slow to flow. I like the fact that that rhymed. And water is very unviscous or not viscous at all because it runs very quickly. Flammability, obviously that's to do with how readily something sets alight. Volatility is how readily something turns into a gas. So if we take the various fractions and we make a few comparisons, Let's compare the viscosity, volatility and boiling points of bitumen compared with refinery gases. So clearly bitumen will be more viscous, it will be less volatile and it will have a higher boiling point. It will also have a darker colour because it's a brownish sticky colour, whereas refinery gases are colourless. So do be aware and do be willing to make comparisons and make full comparisons. So say refinery gases are lighter in colour, have a lower boiling point, are less viscous, etc. Cracking now, remember that is a process carried out in order to break large hydrocarbon chains into smaller, more useful ones, and it's all due to demand because effectively the shorter chain hydrocarbons, the shorter chain alkanes and alkenes make much better fuels than the long chains, which is why we carry out cracking. Do remember that you need a high temperature, which is between 600 and 700 degrees Celsius, and you need an alumina or silica catalyst in order to speed up the process. Let's touch on a few reactions that you need to be aware of.
We could ask you what is the test for an alkene or an unsaturated hydrocarbon. That's actually the same question. So effectively you're testing for the presence of the C double bond C. What you'd write as your answer is that you add bromine water, and in terms of your observations what you would see is that it would go from orange to colourless. Let's actually look at an example. So we'll take ethene. We're adding bromine water. Remember bromine is diatomic, hence why I'm saying Br2. And then what happens is the double bond breaks, meaning that there are two available spaces for bromine to join on, which is here and here. And there's no byproduct because of that. And because bromine simply added itself, you say that this is an addition reaction. So what is the type of reaction? Addition, you add bromine water and it turns from orange to colourless. Now looking at alkanes reactions with bromine water. So alkanes or a saturated compound, it's basically the same thing. What you see this time, I'm going to take methane as my example, but I could have used ethane or propane. We add it to bromine water. But what happens this time is one of the hydrogen pops off, the bromine joins, you complete the rest of the molecule, and what you have left over is clearly a hydrogen that's just left methane and another bromine atom, which is why this is your equation here. Because all that's happened is that hydrogen has simply been swapped or substituted for bromine, we say that this is a substitution reaction. So you can actually see what's happened here. Looking at the alcohols now, notice that their functional group is OH, and do remember that each oxygen atom can form two bonds, while hydrogen obviously forms only one, so we'll bear that in mind now. So starting with the most simple version, which contains one carbon, its name, one carbon, so meth is an alcohol, so it's methanol. In terms of drawing it, draw your functional group coming off first. I've already told you it forms two bonds when you're talking about oxygen, and then just fill up with hydrogens. And that is methanol. Two carbons now, so two meaning it's eth, so ethanol. This is the alcohol found in natural alcoholic drinks. So we need two carbons. Here's our functional group, the OH. Filling up with hydrogens, there's ethanol. Three carbons, so alcohol, propanol. Do notice there is a second isomer of propanol, because actually what I've drawn here is propan-1-ol. But there's also propan-2-ol, so we can actually move the position of that alcohol functional group to be on the second carbon here, and then just fill up with hydrogens. Try and draw your hydrogens better than I am, these don't even look like H's.
So how can alcohols be oxidized? Firstly, you can burn them in air, which we would call combustion, because that's burning. Secondly, they just react naturally with the oxygen in air, and that's due to the action of microbes in the air. We call that microbial oxidation. And lastly, you can heat them with potassium dichromate in the presence of dilute sulfuric acid, and that will also oxidize them. So if we're taking ethanol, for example, it will be oxidized to ethanoic acid. So we've taken an alcohol, we've oxidized it, and it has produced a carboxylic acid. Some uses of alcohol aside from use in alcoholic drinks. They can also be used as good fuels and in perfumes, and sometimes you'll see on your perfume bottle it might say alcohol free because many actual perfumes do contain alcohol. Looking at now at the production of alcohol, we need to know the two main ways, which is fermentation and hydration of ethene. So we need to compare both of these methods for making alcohol. So let's first of all look at their raw materials. Hydration of ethene is obviously ethene, so that's going to be from crude oil, which means it's a non-renewable resource, whereas fermentation involves using sugarcane and using your old-fashioned approach, so using yeast in order to ferment that sugarcane to produce the ethanol. So obviously that uses a renewable resource. In terms of temperature and pressure needed, fermentation, that's going to use low temperatures and pressures, whereas hydration of ethene is a very industrial process, so it involves high temperatures and pressures. The type of process involved now, we say that fermentation is a batch process, and that's because you mix together all the reactants and you leave it for several weeks or months. You remove the alcohol and then you start again, hence why it's a batch process. Whereas hydration of ethene is a continuous process because it can just carry on endlessly. As long as you've got the reactants and the reaction conditions, it keeps going. Let's look at our reaction equations now. You've got glucose from the sugarcane, so C6H12O6, and it breaks down using anaerobic respiration by yeast into ethanol plus carbon dioxide, and we know carbon dioxide can be used in bread making. Hydration of ethene is, as the name suggests, adding water to ethene. So you've got C2H4, you add H2O to it, and that's how you produce your ethanol. Lastly, look at the product produced. Fermentation obviously makes a pretty impure product because it's got lots of other things mixed in with it, whereas hydration of ethene makes a pure product. So be aware when they give you an exam question and they give you a situation and they tell you what sort of resources are available, whether there's lots of electricity available, that sort of thing, be aware of which method would be better to use.
Right, let's look at the carboxylic acids now. They have a more complicated functional group, which is COOH. Do notice in the top right corner that this actually looks like a C with a double bond to the O, and then a sort of alcohol group coming off the bottom of it. So one carbon, because it is a carboxylic acid, we're going to start with meth because it's one carbon, but it's methanoic acid. In terms of drawing it, draw that carbon, draw the functional group, and now just count up and make sure you've got enough bonds coming off the carbon. So far it has 3, we know it needs 4, which is why it just needs a single H here. Looking at 2 carbons now, so that means it's F, so it's ethanoic acid. 2 carbons next to each other, here's our key functional group. Fill up with hydrogens where necessary, and that is ethanoic acid. Looking at the 3 carbon version, so propanoic acid, 3 carbons in a line. There's your functional group. Fill up with H's. This question is about alcohols, carboxylic acids and esters. The table gives information about some alcohols. Complete the table by giving the missing information. Right, so we've got C4H9OH. So remember, your mnemonic is monkeys eat peanut butter to help you remember the names. So we're dealing with the 4th one. So it starts with bute. It's butanol. We now need to provide an estimation for the relative formula mass of ethanol. So use your periodic table, it will tell you that carbon is 12, so we do times 2, plus 5 lots of hydrogen, which is 1, plus oxygen 16, plus hydrogen, which is 1, to get an answer which is 46. Ethanol can be oxidized to ethanoic acid by heating with potassium dichromate 6 and another reagent. Name the other reagent. This is something you just need to learn. It's sulfuric acid. State the colour change that occurs during this reaction. It turns from orange to green. Alcohols react with carboxylic acids to form esters. Name the ester that forms when ethanol reacts with ethanoic acid. So remember, the first part of the ester name comes from the alcohol, which is why it's ethyl. Second bit comes from the carboxylic acid, so it's ethanoate, because remember that's the ending on the ester. Complete the equation for the reaction between methanol and ethanoic acid. And now we need the ester. I'm just going to show you how we're forming that ester. So here's the alcohol we've been provided with. So in order to form that water molecule, we lose the OH from the carboxylic acid, the H from the alcohol, so then you stick the ends together. So there's the ester structure, so now you can write it out. So you can see that it is CH3, COO, which is the functional group of an ester, followed by CH3. And I do find drawing those displayed formula really help you out here. Now, a polymer is a large molecule formed from many small molecules known as monomers. An addition polymer is formed from many monomers joining together. And the reason we say it's an addition reaction is because there are no byproducts. You're simply adding those various monomers together. Let's take an example now, e.g. the formation of the addition polymer polyethene. So because it's addition polymerization, you need a monomer, which in this case is ethene. Remember that ethene has 2 carbon atoms and it is unsaturated. There's a very specific way of drawing the equation for how this is formed. You then need an arrow, and then effectively you break that double bond, elongate those side bonds, and then add those hydrogen atoms back in. And then you have some all-important square brackets. And now because you've got a large number of these monomers joining together, we're not going to draw them all. We're just going to use a small n to show that there's a lot of them. And that's how you draw polyethene formation. And if we were to name the monomer, we know that that was ethene, and our polymer is polyethene, meaning many ethene molecules joined together. Now this is a version of plastic you'll be quite familiar with because it's used to make things like cling film and plastic bags. Let's take a second example now. So what about the formation of polypropene? Remember that propene consists of 3 carbon atoms, and I'm going to draw it like this and I'll show you why shortly. Let's draw that arrow, then we're going to break the double bond and add all the other atoms back in place. Elongate those bonds and then draw square brackets. Finally add your N, and that is the formation of polypropene. Now sometimes you might actually be given the structure of a polymer and be asked to deduce what the repeat unit was or which monomer it was made from. So for example, polystyrene, which you see in the example below. And so basically you just need to step back and have a look and see where you think that structure is repeating itself. So I can see that it takes place here and here and here and here, and this one's just chopped in half. So you take one of those out effectively, and then you just remove those side bonds here and reinstall that double bond, and you'll have the monomer or the repeat unit from which the polymer was made from. So your answer will look like this. We draw it with that double bond, add back your hydrogen bonds, and don't forget to add that C6H5. Check your bond number, because remember each carbon atom forms 4 bonds, 1, 2, 3, 4, 1, 2, 3, 4, and that is your final answer. Now we're moving on to condensation polymerization. So this is different from addition polymerization. That word condensation tells you that a small molecule is lost in the reaction, and honestly that tends to be water. So the first example we're looking at is the formation of polyester, which is an example of a condensation polymerization reaction. And just to point out the monomers, you need a diol and a dicarboxylic acid. Now a diol is an alcohol, so remember you've got the OH functional group, di meaning 2, so you'll find that that monomer has 2 OH groups on it. The dicarboxylic acid functional group is COOH, again di, so you're going to have 2 of them. So I'll show you the general equation for forming a polyester. So we'll start with our dicarboxylic acid. Here are the all-important functional groups. Notice that we're using a block diagram to represent that carboxylic acid. Please don't worry about this. All the block means is that you have a certain number of carbon atoms in the middle. We're not that fussed about it because after all they're not going to be involved in the reaction. It's only this bit that's important. So we just use that block to represent a set number of carbon atoms. So there's our dicarboxylic acid. Here's our alcohol. Then we're going to have another dicarboxylic acid, followed by another diol. So I've already told you that in a condensation reaction water is lost, but where are those water molecules going to be lost in order to allow our monomers to join together to form our polymer? Well, it's going to happen like this. Remember that water is H2O, so you're going to take the O and the H from the dicarboxylic acid and the H from the diol, so here, and then the same will happen at this point, and again at this point. Always the OH from the dicarboxylic acid and the H from the diol. And then when those water molecules are lost, you're just going to stick together the remaining parts of the molecule. And be very careful with how you draw that adjoining bond. And we're just going to add some dotted lines around the end of that molecule to show that that molecule continues. So here's our polyester. And then to show you that ester bond which is formed, it's here, as you would imagine, because it's where the molecules have stuck themselves together. And that helps to explain why the functional group of an ester is COO. Now, very specific examples given in the specification include PET, which is a polyester. You don't need to know what PET stands for. You could be asked to draw that, and it would be more than fine for you to draw what I've just drawn here, because after all, it is a polyester. So I'm just going to write that here, e.g. PET. Now, one thing I wanted to point out with PET, it's just a random part of the spec, is that it can be converted back into its original monomers and be re-polymerized. We're now going to look at how you would draw a polyamide. Now, polyamides are formed from dicarboxylic acids and diamines. So very similar to what we've just done, we just need to be very careful as to how we draw those monomers. So let's start with our dicarboxylic acid again. So that's COOH functional group. We're going to use a block diagram again to show those carbon atoms in the middle. Then we need the diamine, which has an NH2 functional group. Again, using that block diagram. And then let's draw the same monomers again. So here's our dicarboxylic acid, here's our diamine. Because it's a condensation reaction, we're going to lose the water molecules again. Notice that the OH comes from that dicarboxylic acid again, the H is this time from the diamine. So that will happen 3 times in this particular example, and then just stick together the remaining parts of the molecule. And again, the molecules will continue on either end. And we formed an amide bond here, where all those joins have taken place. Now, the named example of the polyamide you need to know is nylon. If you're asked to draw its structure, you need to draw what I've drawn down here. So we've spent a large amount of time looking at different plastics. Now we need to look at issues with their disposal. Now, plastics are difficult to dispose of because they are unreactive, they are inert. So what methods of disposal exist? And what are their various advantages and disadvantages? Firstly, obviously landfill. Plastics occupy landfill. Now, the advantage of using landfill is, first of all, it's cheap and that no greenhouse gases or toxic gases are produced. Disadvantages, they're ugly, smelly, noisy. No one wants to live close to one. They use large areas of land up and the waste will be there for thousands of years. How about if we were to incinerate our plastics, so burn them? Well, the advantage is that it requires little space and it can produce heat used by local homes, offices, as well as being used to produce electricity. However, many disadvantages. First of all, it's expensive to build and maintain the plant. It produces toxic and greenhouse gases, and lots of ash is produced which still needs disposing of in landfill. One other thing to point out is that with any of these things which are dumped, whether it's ash or just the straightforward plastic, as well as being dumped in landfill, it could also be dumped in oceans, which is obviously going to destroy aquatic organisms. Now proteins, we've talked about polyamides. Now proteins are natural polyamides, and the monomer from which they're formed is the amino acid. So let's draw the structure of an amino acid now. It has a central carbon atom, a carboxylic acid functional group, the amine functional group, and then importantly it has an R group which is variable, and that gives the huge diversity of amino acids that exist within the natural world. So the R is different types of side chain. If you're asked to draw the structure of a protein, again you can use a block diagram. So I'm using 3 amino acid block diagrams to demonstrate this. As it's a condensation reaction, we're going to lose that water molecule again. I'm using 3 different colours here to show you that we had 3 different amino acids, and now stick those monomers together. And here I've just shown some elongated bonds here just to show that that protein molecule continues. Here's the amide bond again, and I'm just going to point out that this was a condensation polymerization reaction again. Let's do a list of apparatus and be familiar with recognizing them and potentially drawing them. So first of all, our Bunsen burner. The easiest way to draw that is with an arrow going upwards with the word heat underneath. With chemistry, it's not an art competition. It's not about how well you can draw stuff. You need to draw it in a very scientific way. So the tripod, remember that's what you heat stuff on, will look like this. And on top of the tripod often sits a gauze, which lots of people pronounce that quite strangely. That's how you say it and that's how you spell it. And then that often sits on top of a heat-proof mat. And then while I'm at it, I might as well put an evaporating basin on the top so I don't have to draw it later. Your beaker is very basic, hopefully less wobbly than that. You have a conical flask, which is more triangular at the bottom. If you're carrying out a filtration technique, remember that's separating an insoluble solute from a solvent. You're going to use a filter funnel, which tends to sit atop a beaker, and you need filter paper in there. Measuring cylinders, remember they're used to measure out inaccurate volumes of liquids. Something like this is more than adequate. Scales are used to measure the mass or weight of objects. You might use a thermometer if you're needing to find out the temperature. And a stopwatch is good when you're looking to measure rates of reaction, for example, so the time it takes to evolve 100 centimetres cubed of gas, for example. That's going to look very similar to your scales. Do notice, although I've already pointed out the measuring cylinder is a very inaccurate way of measuring volume, you've got far more accurate ways using pipettes, so like a glass pipette that you use in titrations. That will accurately measure out 25 centimetres cubed of liquid, for example. And then you have the very long, skinny burette. I really don't think you'll be asked to draw this. Remember that has a little tap and that measures out extremely precisely.
Looking at solutions now, so be aware of the solution words you need to know and their definitions. So we're going to use coffee being dissolved in hot water as our example so that you can actually understand the words I'm saying. So we're trying to make a nice cup of coffee and we're going to start by looking at what a solute is. So a solute is a solid which dissolves in a solvent. So in the case of our coffee example, the solute is the coffee grounds. The solvent is the liquid in which the solute dissolves. So in our example, that would be the hot water. The solution is the mixture of the solvent and solute. So that would be the nice cup of coffee that we make. And then a saturated solution is one where you can't dissolve any more solute into the solvent. So it's at its maximum capacity effectively.
Now, there are lots of different reasons why you carry out a titration. One could be that you want to produce a soluble salt which contains ammonium, potassium or sodium. Because of the way in which the soluble salts dissolve, you need to use a titration in order to work out very accurate volumes of both reactants. So that could be one reason why you want to carry out a titration. Another reason you want to carry out a titration is because you want to carry out a titration calculation in order to find out an unknown concentration. Now, I'm not going to talk about that in too much detail here because the whole point of this video is to show you the method used. You need to watch my alternative video on titration calculations to understand the maths involved. But what Amelia and I are focused on doing today is showing you how to accurately carry out titration and to accurately find the volume of hydrochloric acid needed to neutralize a particular volume and concentration of sodium hydroxide, because that's really what a titration is. It's adding a very specific volume of one reactant to another, causing a neutralization reaction to take place, and we use an indicator in order to tell us the neutralization has occurred.
Okay, so we're going to put hydrochloric acid in the burette and sodium hydroxide in the flask. So I'm going to load the burette with the acid. Usually you wash it with acid 2-3 times, but this time we just do once. So the tap, of course, must be off, closed, and very slowly because it loads very quickly. Otherwise it will overflow. And
notice you can carry out a titration in either way. You could have the acid in the burette or the acid in the conical flask. Just depends on which indicator you're using.
Okay, because I want to start from 0, I'm going to lose a bit of acid in the beaker and also to get rid of the bubbles that sometimes forms in the tap. That's it.
Perfect. In order to avoid parallax errors, you need to make sure you read from the bottom of the meniscus, because if you look at liquid in a particularly narrow tube, you notice that it has a very curved shape, so you need to read from the bottom of what's known as the meniscus.
Then you add the sodium hydroxide to the flask, which has been previously washed with sodium hydroxide solution.
Multiple washing.
So this is 25 cubic centimeter of sodium hydroxide.
This is a glass pipette and it's used to produce very accurate volumes of solution.
Okay, then you add a drop of methyl orange.
So methyl orange is an indicator which, as you can see, turns orange in an alkaline solution. Remember that sodium hydroxide is strongly alkali.
And then I place it.
Yeah, so we're ready to begin our titration. Notice that the end point, that's when neutralization occurs, is when the methyl orange turns from orange to red. The whole point of using these indicators is they have a very sharp end point. They have a sharp change in colour, which is why methyl orange, phenolphthalein, they're both ideal for use in titrations. Universal indicator is inappropriate because remember it shows a range of different colours. So Amelia is going to open the tap and start slowly adding hydrochloric acid to the sodium hydroxide. The beauty of a burette is that it can add drop by drop. So it makes it far more accurate than a measuring cylinder or a beaker. She's swirling the flask in order to mix the contents. So we place the tile underneath the flask in order to observe the colour change.
When now you have the drop, you will see pink and then disappear.
Yeah.
So it's not ready. It doesn't mean that that is the end point, because it must be a color that doesn't disappear when you swirl the flask.
Yeah.
See? The pink starting to appear and then disappear. So it means that we are close to the end point.
Mm-hmm.
Oh, that's it.
Oh yeah, it is pink.
This is the color we want.
So we've reached our end point. The solution, although it looks pink, in your exam you're going to have to say that it's red, and that means that the solution is slightly acidic. So the essential thing now is that we read the volume of the acid that was added. Notice that the burette runs from 0 centimeters cubed down to 50. So we're really trying to work out what this volume is here. So
yes, it's 25.
Yeah, so reading from the bottom of the meniscus, we can see that 25 centimeters cubed of acid was added.
So if you have this color, it means that you have been further.
We've already met chromatography earlier. Remember, it tends to be used as a separation technique to look at dyes and inks and food colourings. But we can also use it in this topic to to look at the hydrolysis products of both carbohydrates and proteins. The only thing that makes them slightly tricky is that they're both colourless, and remember, dyes and inks contain lots of colour, which is why they're really useful in chromatography. So in order to cope with the fact that they're colourless, we need something called a locating agent.
Our last separation technique is chromatography. Remember, this is used to separate liquids of different solubilities, so that could be food colouring, dyes, inks, for example. Be prepared to describe how you set up a chromatogram. Remember, you have filter paper, which you draw a reference line on in pencil. You put the dots of ink along the pencil line, and then you dip the paper into water. As the water soaks up, it draws the dyes up the paper, and you can determine several things from that. So first of all, notice that you draw the reference line in pencil. Why? Because you don't want the pencil to spread and go flowing up the paper too, because that will disrupt your chromatogram. Notice that the ink which travels the furthest has the highest solubility, which kind of makes sense. And be prepared to use the formula, which is the RF formula. And that's the formula whereby the distance travelled by the component is divided by the distance travelled by the solvent. We now need to touch on separation techniques, so I'm going to give you all the different examples and how you would use each of them. So first of all, filtration. You are going to use this to separate an insoluble solute from a solvent. And your example here could be sand and water. The reason filtration works so well is you pour the mixture through the filter funnel containing filter paper, and what you'll find is the sand stays in the funnel, the water flows through into the beaker below. So you've separated your insoluble solute from the solvent. And be prepared to label all the apparatus involved and be able to draw simple diagrams. Getting slightly more complicated now, we now have a soluble solute that needs separating from a solvent. This could be something like salt being separated from water. So clearly filtration won't work because the salt will go straight through into the beaker below, which is why we need to use evaporation. So you have a tripod with gauze on the top, an evaporating basin containing the salt solution. You boil using a Bunsen burner. The excess water boils off and you're left behind with salt in the evaporating basin. Next up, we're separating immiscible liquids. So these are liquids which do not mix. A good example here is oil and water. And you will find that oil, and you can see this at petrol stations, if for some reason it's rained and then petrol's ended up in the puddle, you can see the petrol floating on top of the water, and that's what happens with oil too. So in this case, you can just put it into a funnel, you can open a tap and the water will drain out first, close the tap and you'll leave the oil behind in the funnel. Now liquids of different boiling points, for example ethanol and water. Clearly evaporation and filtration won't work here, and this is where you use simple distillation, and simple distillation relies on the fact that liquids have different boiling points, because what happens is you use a Bunsen burner to boil the mixture of liquids, and the liquid with the lower boiling point will evaporate first. So that would be the ethanol with a boiling point of 78 degrees Celsius, leaving behind the water below. And if you have a real mixture of liquids with lots of different boiling points, such as crude oil, this is where you'll use fractional distillation, which actually allows you to separate out many different liquids of different boiling points. When we look at a pure substance, this is a substance which contains only one type of material. So that could be, for example, one element, so carbon, or it could be one compound, such as carbon dioxide. But the point is there's nothing else in there contaminating it. If you think you have a pure substance and you want to look at its boiling point, be aware that a pure substance will have a fixed boiling point and should not boil over a range of temperatures. If it boils over a range of temperatures, as crude oil would, it's a mixture, it is not a pure substance. So the test for hydrogen, don't say it's the squeaky pop test, you won't get a mark for that. You need to say that you hold a lighted splint over the gas, and if hydrogen is present, there should be a squeaky pop. With oxygen, you need to say that it relights a glowing splint. Carbon dioxide, remember, turns lime water cloudy. Chlorine bleaches damp litmus paper. And ammonia turns damp red litmus paper blue. Now I've given you the most concise, precise definitions for this. So make sure you've learnt them. Every single word matters here. So for example, damp is worth a mark, red litmus paper, worth a mark. So make sure you learn them properly. And now we're getting more complex and we're going to look at flame tests. So remember, if we have an unknown metal ion, a flame test is a good way of working out what that metal was. So in terms of carrying out a flame test, remember that you're going to use a clean nichrome wire, which is, you could clean it using hydrochloric acid, but the point is you don't want any contaminants on the end of that nichrome wire. Then you dip it in the sample to be tested and then hold it in a roaring blue flame, and that is key. You can't be adding it to a yellow sooty flame. That won't work because the yellow will obstruct the colour. So hold it in a roaring blue flame. So the colours. Now if we've got lithium ions, you will see a lovely red crimson colour. Sodium, you'll see a yellow flame. And potassium, as with when you add it to cold water, you will see a lilac flame. Calcium goes an orange-red colour or a brick-red colour, and copper goes a blue-green colour. If you don't want to carry out a flame test, you can use a precipitation reaction, and you can look at the colour precipitate formed once you've added sodium hydroxide. So if you add sodium hydroxide to something containing copper, you will see a blue precipitate formed. Iron 2 will form a green precipitate, and iron 3 will be a brown precipitate, and I remember those because they're kind of muddy, earthy colours, so it goes green for iron 2, brown for iron 3. Testing for ammonium ions now, which is NH4+, again add sodium hydroxide. You won't see a precipitate form in this case. Instead, a stinky gas will be released, which should be ammonia, and you test for the presence of that ammonia using the method I've already described, which is that it should turn damp red litmus paper blue. Okay, moving over now to test for negative ions. We've looked at metal ions and ammonium, so we're looking now at the halides, which is group 7, the halogens. So first of all, you need to add nitric acid. You add that dilute nitric acid in order to remove any carbonate ions which might interfere with your test. Following that, you add silver nitrate, and then you'll end up with a range of precipitates. So looking at the chlorides, if you add chloride ions to silver nitrate, you produce silver chloride, which is a white precipitate. If you add silver nitrate to something containing bromide ions, you make silver bromide, which is a cream precipitate. And lastly, adding silver nitrate to something containing iodide ions will produce a yellow precipitate. So notice those colours get darker. We go from white to cream to yellow. And be prepared to write the ionic equation for this, which will be, for example, with chlorine, it will be Ag plus Cl minus forms AgCl solid. Thank you so much for watching my video. Well done if you made it to the end. Don't forget you can buy my Science with Hazel Perfect Answer revision guides on my website. They're available right now.